Muy buenos días tengan todos ustedes y sean bienvenidos al Teatro del Complejo Cultural Universitario, donde hoy, lunes 4 de abril de 2011, se llevará a cabo la inauguración del seminario y taller internacionales plural de Resonancia Magnética Nuclear en Sonidos. Para dar inicio a este evento, presentaremos a las autoridades que hoy nos acompañan. Encabezadas por el representante personal del rector de la UAP, del doctor Enrique Agüera Ibáñez, nos acompaña el maestro Jaime Vázquez López, vicerrector de Docencia de la UAP. Así también se encuentra con nosotros el director del Centro de Nanociencia y Microtecnología del Instituto Politécnico Nacional, el doctor Gerardo Cabañas Moreno. Se encuentra con nosotros el doctor Ricardo Vera Graciano, director del Instituto de Investigaciones en Materiales de la UNAM. Saludo a la presencia del doctor Jean-Paul Lamoureux, investigador de la Universidad de Ciencias y Tecnologías de Lille, Francia. Se encuentra con nosotros el director del Instituto de Física de la UAP, el doctor Juan Francisco Rivas Silva. Así también saludo a la presencia de invitados especiales y funcionarios de la universidad. Dejo el uso de la palabra al doctor Juan Francisco Rivas Silva, director del Instituto de Física Luis Rivera Terrazas de la UAP.
Muchas gracias. Buenos días a todos. De parte de los comités organizadores y de todas las personas involucradas en este evento, les damos la más cordial bienvenida a todos, desde profesores e investigadores de otras instituciones, como de los propios de nuestra universidad. En particular, reciban un saludo de la comunidad del Instituto de Física Luis Rivera Terrazas de esta institución. Agradecemos mucho la presencia de los miembros del Presidium, del maestro Jaime Vázquez, vicerrector de Docencia, del doctor Jean-Paul Lamoureux, expositor principal de este evento, profesor de la Universidad de Lille en Francia, del doctor Ricardo Vera, de Materiales de la UNAM, del doctor Gerardo Cabañas, del Politécnico. Quisiera mencionar la labor conjunta de muchas otras personalidades, entre otras que sin su apoyo no hubiera podido ser posible la organización de este evento, del nuestro señor rector, el doctor Enrique Agüera Ibáñez, del doctor Pedro Hugo Hernández, vicerrector de Investigación, del maestro Rafael Hernández Oropesa, director de Relaciones Internacionales, del maestro Javier Rodríguez, Francisco Javier Rodríguez, también de Relaciones Internacionales, del maestro Albert Nichtboer, coordinador de proyectos internacionales y responsable de los proyectos de una de las dependencias que inició todo este evento, que es el Erasmus Mundus de la Comunidad Europea. De la licenciada Angélica Castillo, directora de Cooperación Académica de la UNAM, del licenciado Rodríguez Flores Gutiérrez, también de la UNAM, de muchos otros que por falta de tiempo quizá no voy a omitir, pero no porque no deba de hacerlo, por ejemplo, gente de las empresas Bruker, Yeol y Varian, que nos van a apoyar muchísimo con sus experimentos y equipo. En este evento, como todos saben, se realizará en 2 días de seminarios teóricos aquí en esta sede y de 3 días repetidos en la UNAM y en el Politécnico. Se registraron finalmente alrededor de 240 participantes de esas instituciones, la UNAM, el Politécnico, esta universidad BUAP y de otras instituciones como la Universidad de Durango, universidades de Guanajuato, Yucatán, el Estado de México y demás. Todo ello con el interés de aprender junto con los expertos de Francia y México los fundamentos de esta técnica llamada resonancia magnética nuclear y su versión dedicada al estudio de los sólidos. Para ello todos deberemos de hacer un esfuerzo para entender los fundamentos físicos de la teoría de las interacciones de un campo magnético con los espines nuclear y electrónico y los distintos aspectos que tienen esas interacciones. Por otra parte, los experimentos que se van a llevar a cabo nos enseñarán directamente el uso de equipo altamente especializado para investigar las propiedades de los distintos sistemas, como son los sólidos, las proteínas y otras, y sus distintas aplicaciones en las áreas de la investigación y la tecnología. Esto permitirá concebir a esta área de trabajo científico como un camino complementario a otros que se dedican a escudriñar la estructura microscópica de la materia, pero algunos con más ventajas que otros. Esperamos, pues, muy sinceramente, cumplir las expectativas de ustedes y de los organizadores para satisfacer a su vez a los objetivos de las distintas autoridades que han apoyado esta organización, como puede ser que la investigación de esta área sea desarrollada más en esta universidad y en las instituciones hermanas que nos acompañan. Muchas gracias.
A continuación, dejo uso de la palabra al doctor José Gerardo Cabañas Moreno, director del Centro de Nanociencia y Microtecnología del Instituto Politécnico.
Gracias, buenos días a todos. Maestro Jaime Vázquez, vicerrector académico de la UAP, profesores Amorox, Bonom, Lafont, Tolele, Mendoza, los expositores principales de este taller, a mis colegas de la UNAM y del IPN y de la UAP, aquí presentes y que estarán también durante el seminario, a las compañías patrocinadoras y a todos ustedes los participantes. A nombre de la doctora Yoloxóchitl Bustamante, directora general del IPN, les expreso la satisfacción de estar aquí y de verse realizado este evento que se venía programando desde hace varios meses, con el trabajo muy fuerte, sobre todo de los maestros Francisco Rodríguez y Albert Nichboer. Perdón, Albert, creo que nunca pronuncio bien el apellido. De nuestros colegas de la UNAM y de la UAP. Y quiero expresar también mi agradecimiento al doctor Gerardo Cepeda del IPN, que ha hecho todo el trabajo académico de parte de nuestra institución. En realidad estoy sorprendido por el número de participantes registrados. Cuando primero hablamos de esto pensé que los planes de traer de entre 200 y 300 participantes estaban un poquito estirados para esta técnica y realmente me da mucho gusto haberme equivocado. Creo que el interés por ella se conjuga en diferentes disciplinas y como quizás muchos de ustedes ya sepan y si no algunos van a ir averiguando, esta técnica ha ido evolucionando quizás más o menos en unos 50 a 60 años y actualmente es una de las que quizás tiene posibilidades de desarrollo más grande y de combinar lo que se puede hacer con lo usual con moléculas orgánicas, con materiales biológicos y más recientemente, y el tema de este seminario, con materiales sólidos de diferentes estructuras. Para todos ustedes los participantes, especialmente para los alumnos, creo que este es un evento que no fácilmente se vuelve a organizar de nuevo con este nivel de los conferencistas, dedicados aquí 2 días completos para tratar de darles a ustedes esta introducción a las técnicas avanzadas de resonancia magnética nuclear en sólidos. Les sugiero, sobre todo a los estudiantes, que en estos 2 días le hagan la corte a la resonancia magnética al nuclear. Con un poquito de suerte, algunos de ustedes se van a casar con ella. En estos casos la poligamía está bien, ustedes pueden compartir con otras técnicas y ojalá de aquí salga un impulso fuerte a la resonancia magnética de sólidos, en particular en México. Aprovecho para comunicarles que en el Centro de Nanociencias y Nanotecnología del Politécnico estamos por hacer una adquisición importante de equipo de resonancia magnética nuclear. El centro es un centro que ofrece sus servicios a la comunidad del Politécnico y a la de todo del país en general. Entonces, próximamente, si ustedes quieren ver la página del centro, que es www.nanocentro.ipn.mx, podrán ver algunas de las adquisiciones que en este año seguramente se realizarán y que estarán a disposición de la comunidad científica y académica del país. No me resta más que volver a agradecer a todos los involucrados en el seminario taller. Los esperamos a partir del miércoles en la Escuela Nacional de Ciencias Biológicas, donde va a ser la parte del taller que le corresponde al Politécnico. Y muchas gracias y mucha suerte les deseo. Gracias.
Escuchemos las palabras del doctor Ricardo Veragraciano, director del Instituto de Investigación en Materiales de la UNAM.
Muy buenos días, maestro José Jaime Vázquez López, vicerrector de la Universidad Autónoma de Puebla, de esta benemérita institución que todos apreciamos, compañeros del presidium, compañeros, profesores, expositores, estudiantes que nos acompañan el día de hoy. Es un placer para mí traer un saludo personal del doctor José Narro Robles, rector de la Universidad Nacional Autónoma de México, quien desafortunadamente no nos pudo acompañar en esta oportunidad. Así como señaló también el doctor Cabañas, déjenme decirles a ustedes que es un placer estar aquí viendo este esfuerzo de cooperación entre instituciones académicas de diferentes lugares de este país. Este esfuerzo de colaboración es un esfuerzo importante porque nos permite conocernos un poco más, aprender de una técnica que es la resonancia magnética nuclear de sólidos, que ha avanzado, como decía el doctor Cabañas, de una manera impresionante en los últimos años y que nos permite hacer estudios a todo tipo de materiales, sólidos, geles, líquidos, pero en particular la técnica de resonancia magnética nuclear de sólidos es una técnica que hoy nos abre muy amplias posibilidades para estudiar una gran cantidad de materiales como son las nanoestructuras, materiales nanoporosos, materiales mesoporosos, estructuras biológicas muy interesantes, soportes de diferentes tipos sobre moléculas orgánicas e inorgánicas, en fin. Hay una gran cantidad de aplicaciones que la resonancia magnética nuclear de sólidos nos ofrece. Y ustedes van a ver una visión panorámica de todo esto durante estos días y durante los talleres que se van a celebrar en el Instituto Politécnico Nacional y en el Instituto de Investigaciones en Materiales de la UNAM. Quiero dar un saludo también de parte del doctor Eduardo Bárcena, director de la Facultad de Química de la UNAM, y del doctor Gabriel Cuevas, director del Instituto de Química, que participan por parte de la UNAM con nosotros en este evento. No me queda más que agradecerles a los expositores que van a dar estos cursos, todo el ánimo que ellos tienen para transmitir sus conocimientos a las personas que vienen representando a diferentes empresas que se dedican a la resonancia magnética nuclear también. Un saludo para todos ustedes y para los compañeros, estudiantes y profesores que atienden a este taller y seminario. Mis más sinceras felicitaciones y les deseo el mejor de los éxitos. Muchas gracias.
A continuación doy con uso de la palabra al maestro Jaime Vázquez López, vicerrector de Docencia y representante personal del doctor Enrique Agüera Ibáñez, quien al final de su mensaje inaugurará este seminario.
Gracias. Muy buenos días a todos ustedes. Bienvenidos a nuestra universidad. A nombre del rector, doctor Enrique Agüera Ibáñez, espero que estos 2 días de intenso trabajo sean fructíferos en todo sentido. Ya mis antecesores, que están en la mesa de honor, señalaron del esfuerzo de colaboración que ha significado el llegar a este evento. Yo tengo copia de la correspondencia que amablemente me hizo llegar Albert durante meses, Francisco, y del intenso trabajo que significó el que estemos hoy aquí por inaugurar un evento. Es un gusto también tener a tantos jóvenes, regularmente no se tiene esa respuesta. Hoy hicimos un esquema que también agradezco a Albert y al maestro Germán Pérez de la Dirección de Apoyo al Estudiante de la Vicerrectoría, que impulsaron estas posibilidades y que hoy nos permite tener, sobre todo a los muchachos, a quienes espero puedan aprovechar al máximo este evento. ¿En qué se enmarca este esfuerzo? Bueno, hay que reconocer aquí los proyectos de cooperación transatlántica del Erasmus Mundus. Es justo también dar las gracias y bienvenida al doctor Jean-Paul Amoreau, profesor investigador de la Universidad de Ciencias y Tecnologías Lille I de Francia, quien acogió la iniciativa para la organización de este encuentro. Es un privilegio contarlo como ponente principal del seminario, como un gran experto reconocido a nivel mundial como es el doctor. Es preciso señalar que la Universidad de Ciencias y Tecnologías de Lille I tiene la amabilidad de ofrecer 3 plazas de doctorado para la formación de expertos en resonancia magnética nuclear de sólidos provenientes de las instituciones organizadoras de este seminario. Vemos así que se produce una fructífera cooperación entre México y Francia y que mientras que en el ámbito político pueden presentarse diferencias entre ambas naciones, los académicos y científicos mantenemos esfuerzos para establecer y afianzar vínculos orientados al desarrollo de la ciencia. Igualmente, deseo mencionar que el programa Erasmus Mundus Ventana para México, el lote 18, financiado por la Unión Europea, ha facilitado la movilidad inicial del doctor Amoreau y con ello el desarrollo de este proyecto de colaboración. En el marco de Erasmus Mundus, nuestra universidad ha recibido un total de 43 becas completas, cubriendo viajes, hospedaje, alimentación y seguro médico para estudiantes y profesores investigadores. A través de estos apoyos ha sido posible la participación de 10 estudiantes indígenas pertenecientes a diversas etnias y grupos en situación de vulnerabilidad en programas de intercambio que han impulsado su movilidad social en un proceso que incluso ha recibido reconocimiento de la propia Comisión Europea. Por otra parte, agradecemos a nuestros patrocinadores, la empresa Bruker Biospin, representada por el doctor Jochen Mestrup, a Agilent Technologies, representado por el químico Ramón Rosales, y la firma Geol, representada por el doctor Yusuke Nishiyama, a quien por su conducto queremos hacer llegar al pueblo japonés las condolencias y la solidaridad de los universitarios ante los desastres naturales y la crisis nuclear que sufre ese país. Desde 1946, cuando los científicos Bloch y Purcell observaron una señal de resonancia magnética nuclear, descubrimiento que les valió recibir el Premio Nobel de Física, la RMN, como se conoce, se ha convertido en una herramienta indispensable para la determinación de estructuras. Su utilización en sólidos ha significado un avance más que brinda importantes posibilidades de investigación para determinar la estructura molecular, las propiedades de materiales, su evolución y el estudio de muestras heterogéneas en general. La resonancia magnética nuclear de sólidos es una nueva disciplina en México y la intención de nuestras instituciones es desarrollar un amplio proyecto a través de una red nacional que impulse la movilidad de estudiantes y académicos y trabaje en la consecución de financiamiento para la realización de investigaciones. Además, los nuevos desarrollos en conceptos, métodos y equipos de esta rama científica hacen necesario el intercambio de conocimientos y experiencias para potenciar su aplicación en diferentes áreas de conocimiento. El Seminario Internacional de Resonancia Magnética Nuclear en Sólidos, que hoy inicia, representa la oportunidad de conocer el trabajo de expertos en la materia de gran prestigio nacional e internacional, además de que permitirá la elaboración de materiales didácticos para los profesores y estudiantes participantes. De ahí la trascendencia de este encuentro, que a la par del debate académico apoyará la formación de especialistas en la materia. Pido a todos ustedes, por favor, ponernos de pie para pasar a la parte protocolaria. A nombre del rector de nuestra universidad, doctor Enrique Agüera Ibáñez, hoy lunes 4 de abril, declaro formalmente inaugurado el Seminario y Taller Internacional Plural de Resonancia Magnética Nuclear en Sólidos, esperando que alcance sus objetivos y contribuya al desarrollo de todos los participantes. Muchas gracias, buenos días.
Y es así con la intervención del maestro Jaime Vázquez López, como llega a su término este evento protocolario. Declaramos un breve receso para despedir a las autoridades que hoy nos acompañan. No sin antes recordarles que a todos los asistentes en la parte posterior habrá unas mesas donde habrá unos traductores para quien quiera utilizarlos. Gracias.
Al primer conferencista, el doctor Guillermo Mendoza Díaz. Él se doctoró en la UNAM, hizo un postdoc en Leiden, Holanda. Es miembro del Sistema Nacional de Investigadores, nivel 2. Tiene en su haber aproximadamente 50 publicaciones internacionales y actualmente es director del Departamento de Ingeniería Química, Electrónica y Biomédica. Ha sido coordinador de posgrado en Química y sus líneas de investigación son alrededor de la química de coordinación y bioinorgánica en materiales, RMN de líquidos y sólidos, y ha sido profesor visitante en el Imperial College y la Oregon State University. Tiene algunos alumnos graduados y pues le vamos a agradecer al doctor Guillermo Mendoza por acompañarnos, por aceptar esta presentación, que solicitamos que fuera en español para que muchos de ustedes que no han tenido una interacción con la RMN de sólidos, pues sea esta plática para ponerlos en antecedentes de una manera muy amena, con la enorme experiencia que tiene el doctor Mendoza en el campo. Bienvenido y adelante.
Muchas gracias. Muchas gracias. Gracias por la invitación. Y bueno, siempre he dicho que yo no soy un especialista en resonancia, simplemente estoy un poquito viejo y algo de experiencia he tenido con ella. Nosotros hemos estado trabajando con resonancia desde 1994 y en la resonancia de sólidos, digamos que desde 1996, ya con un poquito más de intensidad. Esta plática lo que pretende no es, para aquellos que hayan estado viendo un poco la presentación que mandé, no es una plática difícil. Lo que queremos es entender cuáles son las cosas, qué tipo de efectos están involucrados en el fenómeno de resonancia y cómo en algún momento yo me quiero deshacer de ellos y cómo en otro momento quiero que estén presentes. Me gusta estarme moviendo, entonces déjenme tomar el otro micrófono. Sí me oyen, ¿verdad? Ok, entonces lo que es principios básicos de resonancia magnética nuclear, yo voy a partir del supuesto que todos ustedes al menos saben lo que es los principios básicos de resonancia magnética en líquidos, es decir, conocen el efecto Zeeman, saben del desplazamiento químico, del acoplamiento J y básicamente digamos que esos son los conocimientos que yo necesitaría que alguno de ustedes tenga. Para poder describir esta técnica de resonancia y sus principales interacciones, pues hay algo, lo que vamos a ver en esta plática va a ser justo esto, y voy a platicar de dos secuencias básicas para dar, así digamos, los antecedentes necesarios para que después podamos entrar a lo que nos van a venir a platicar los profesores. Y simplemente para empezar y para tener una idea, en resonancia magnética nuclear de sólidos yo puedo tener espectros tan bonitos como un espectro en donde tengo una resolución bastante grande y el objetivo de todo lo que voy a estarles platicando ahora es cómo puedo llegar a este tipo de resolución. Para 1973, básicamente para que tengan también una idea de cuándo estamos hablando de qué tan vieja es esta técnica, se reportó el espectro del benceno y del adamantano en estado sólido utilizando una técnica que todo mundo que trabaja sólidos dice CP+, o la polarización cruzada. Y un poco lo que yo espero es que al final de esta plática ustedes tengan claro que eso no tiene nada de esotérico, que es algo bastante sencillo y que es, digamos, el punto clave con el cual ustedes van a iniciar el conocimiento de la técnica de sólidos. Actualmente, también otra de las cuestiones que es importante es cuando uno piensa en resonancia magnética nuclear y habla de soluciones, pues el primer punto que tengo de limitante es si mi producto es soluble o no. Y si yo tengo un producto insoluble, pues ya perdí la posibilidad de caracterizarlo. Entonces, una de las cuestiones que creo que hace la gran diferencia es pensar que la resonancia de sólidos, yo puedo estudiar prácticamente cualquier material, desde un catalizador o un soporte de catalizador, como podría ser sílice o un silicoaluminato, una zeolita, una piedra, ¿sí? O puedo utilizarlo para ver moléculas sencillas, que digamos que en algún momento uno puede estar interesado en qué tan diferente puede ser el comportamiento de una molécula en solución o en estado sólido. ¿Sí? No necesariamente voy a estar viendo lo mismo, puedo estar empezando a ver interacciones distintas, conformes diferentes, que en algún momento dado puede ser importante estudiar. Obviamente para polímeros, proteínas o membranas celulares es una de las cuestiones que tienen mayor aplicación. Alguna vez cuando yo empecé a conocer esta técnica, una de las cosas que me sorprendió muchísimo era, por ejemplo, ver el espectro de fósforo de una hoja viva. ¿Sí? O sea, imagínense enrollar una hojita de una planta, meterla en el tubito de resonancia, que vamos a ver más adelante cómo es, y estar viendo cómo ese fósforo va cambiando en los diferentes metabolitos mientras la hoja va muriendo. Eso y sin destruir la hoja. Entonces, eso es una técnica que tiene gran potencial. Ok, ¿qué es lo que vamos a poder ver? ¿O qué puedo ver? ¿Qué puedo hacer con la resonancia magnética nuclear? Bueno, obviamente yo puedo caracterizar compuestos como lo caracterizo o como hago un espectro normal en sólidos. Es decir, yo quiero ver si tengo aldehídos, si tengo grupos aromáticos, si tengo metilos, etilos. Es una de las cuestiones típicas y digamos la más sencilla. Puedo medir distancias internucleares. Eso es una cuestión importante, porque a partir de distancias internucleares yo puedo incluso ser capaz de elucidar estructuras tridimensionales en sólidos. Y esto hace una ventaja gigantesca. Durante mucho tiempo en resonancia magnética nuclear, uno de los grandes desarrollos que se ha generado es la elucidación de estructuras tridimensionales de proteínas en solución. Pero uno de los grandes problemas que se tiene cuando uno habla de proteínas en soluciones es verdaderamente la estructura que yo tenía cuando estaba pegada en la membrana. Y una de las cosas que necesito yo es poder comparar qué tanto una proteína cambia de estar en solución a estar en sólido, por ejemplo. Y esto ya es posible hacerse. Puedo también hacer estudios de anisotropía magnética, es decir, yo puedo, por ejemplo, si yo tengo una estructura de rayos X, y de esto en la segunda plática les presentaré algún ejemplo, yo puedo a través de la estructura de rayos X ver cómo está distorsionada o qué tan simétrica es una molécula. ¿Sí? Pero si yo no tengo estructura de rayos X, pues no tengo mucha información. Y a veces es muy interesante saber cómo es la anisotropía de un material para poder determinar diferentes propiedades físicas, como podría ser propiedades ópticas en una dirección o en otra, propiedades piezoeléctricas, etcétera. Bueno, y podemos ver ángulos de torsión, orientaciones atómicas y cuestiones ya más complicadas como es difusión de spin. Imagínense en un material cómo es que yo puedo empezar a analizar cómo el spin camina a través del material. Esto me va a dar información de cómo el material puede enviar información de un lado a otro. Esto obviamente en propiedades físicas es muy importante. Puedo hablar de dinámica molecular. ¿Qué es esto de dinámica molecular? Pues puedo ver equilibrios. Yo estoy muy acostumbrado, por ejemplo, a oír el equilibrio ceto-enol en solución. ¿Pero alguna vez alguno de ustedes ha oído del equilibrio ceto-enol en sólidos? Estudiarlo es posible también. Y bueno, Procesos de intercambio en general también son de las cuestiones que podemos estar viendo. Algo que de una vez les voy a estar platicando es, ustedes también recuerdan en solución, pues todos conocen los tubos de resonancia, que son los tubitos largos de vidrio, y la pregunta es, ¿y en sólidos cómo pongo la muestra? Bueno, para poner la muestra se utilizan rotores como estos, de muy diferentes diámetros, en donde el material puede ser nitruro de silicio, circonia, materiales cerámicos de alta resistencia. Y si se fijan de manera comparativa, pues vean los tamaños que pueden ser comparados con una moneda de 20 centavos. Ok, un poco lo que vamos a ver ahora es también algo que es bien importante. En resonancia de sólidos, a diferencia de resonancia de solución, yo voy a hacer una diferencia entre núcleos sensibles de núcleos insensibles. En resonancia de solución yo manejo normalmente el espectro de protón y mucho de protón, y ese es mi espectro sensible. Pero ya después, cuando hago una resonancia de carbono, la verdad es que no me pongo a pensar si es sensible o insensible, trabajo con ella normalmente. Tampoco me pongo a pensar en la densidad que tengo de carbono 13 comparada con la de carbono, con la de protón en solución. Trabajo con ellos normalmente sin cuestionarme mucho las abundancias relativas. Sin embargo, los efectos y las características que tienen los materiales cuando están en sólidos se vuelven muchísimo más grandes debido a que no existe ese factor de dilución que yo tengo en las soluciones. Y entonces yo voy a tener núcleos de poca abundancia y núcleos insensibles, es decir, núcleos que la constante giromagnética es baja, como podrían ser carbono 13, nitrógeno 15, que van a interaccionar o que van a tener efectos o van a sentir la influencia de otros núcleos de manera diferente a si yo tengo un núcleo sensible como sería protón. Y esto me lleva a que yo voy a tener interacciones presentes en el estado sólido que de hecho también las tengo en solución, pero en solución me van a desaparecer por diferentes efectos. Y entre ellos yo tengo el acoplamiento dipolar heteronuclear, tengo la anisotropía del desplazamiento químico, es decir, cuando yo hablo de desplazamiento químico en solución, yo digo el aldehído aparece en 8.5 y por ahí, ¿sí? Y nunca me pongo a pensar si va a aparecer en 8.7 dependiendo de la orientación que esté en la solución. ¿Sí? Nosotros tenemos que en la solución las moléculas se mueven muy rápido y por lo tanto siempre las estoy tratando como esferas. Y cuando digo una esfera estoy diciendo que es un sistema totalmente isotrópico. Es decir, no depende de la orientación de la molécula el efecto que está sintiendo la molécula por el campo magnético externo. En cambio, cuando yo tengo un sólido, ese sólido no puede girar. Y si yo tengo un benceno que está perpendicular al campo magnético o paralelo al campo magnético, voy a tener desplazamientos químicos diferentes. Y eso es un problema, porque yo lo que quiero es ver el desplazamiento químico del benceno, el único, el isotrópico. Entonces, ¿cómo le voy a hacer? Bien, también voy a tener la posibilidad de ver un acoplamiento dipolar homonuclear. Este acoplamiento dipolar homonuclear, si yo lo que estoy haciendo es estudiando carbono 13, pues no tengo problema. ¿Por qué? Porque carbono 13 en una muestra normal, la probabilidad de tener un carbono 13 junto a otro es de 1 en 10.000. Entonces prácticamente no las voy a tener. En cambio, si yo quisiera ver protones, el acoplamiento homonuclear es un problema gigantesco. ¿Por qué? Porque la mayor parte del ambiente en un polímero, en un material, van a ser muchos protones y van a estar muy cerca unos de otros. Y bien, algo de lo que voy a platicar muy ligeramente es que también incluso el acoplamiento J, el acoplamiento escalar, puede resultar en tener anisotropía y eso me genera problemas, me genera algunas características. Bien, cuando yo hablo de este tipo de interacciones, de estos efectos, en realidad lo que estoy diciendo es de diferentes contribuciones energéticas a una energía que me da como resultado una señal en el espectro. Esa suma de energías o esa suma de contribuciones yo le llamo perturbaciones, un poco por la teoría de perturbaciones en mecánica cuántica, que no voy a hablar de ella, no vamos a estar metiéndonos en Honduras. Lo que yo espero es que ustedes entiendan que esto es válido. ¿Por qué? Porque yo voy a tener un componente principal energético y después varias contribuciones de mucho menor grado. ¿Ok? Y esas de menor grado son las que a mí me van a importar más. Ok, ¿qué es lo que tengo? Yo tengo en esa suma de contribuciones, y lo tengo tanto para soluciones como para sólidos, yo voy a tener lo que es el efecto Zeeman, que esto no es más que el desdoblamiento del campo magnético en spin menos un medio más un medio. Sí, esto, espero todos sepan lo que estoy hablando, ¿verdad? Ok, qué bueno. Bien, este efecto es el efecto más importante. Y al ser el efecto más importante, lo que estoy diciendo es el que en la suma de todas las energías que yo voy a tener, es el que más me contribuye, me va a contribuir con un 80-90% del valor de la energía. ¿Ok? Sin embargo, también quiero que se den cuenta de una cuestión, la técnica de resonancia magnética, por muy poderosa que sea, estamos hablando de energías muy pequeñas, y ese desdoblamiento de Zeeman es del orden de 10 a la menos 20 joules por mol, o sea, 10 a la menos 20 joules por mol. Estamos hablando de energías muy pequeñas. ¿Okay? Y las contribuciones que tengo a continuación, pues son todavía, ay, eso se movió, no estaba así, se mueven, son todavía muchísimo menores. Yo voy a tener, por ejemplo, que esta contribución y esta son debidas al acoplamiento dipolar. Es decir, yo voy a estar viendo interacciones dipolo-dipolo debidas a un spin insensible que tiene espines sensibles cercanos, o de los espines insensibles entre ellos, y dependiendo de qué es lo que esté viendo, si yo estoy viendo espines sensibles, pues serían los espines sensibles entre ellos. Después yo voy a tener una contribución que es la anisotropía del desplazamiento químico. Puedo tener también contribuciones debido a, si yo por ejemplo tengo un nitrógeno 14 unido a un carbono, lo que yo voy a tener es un acoplamiento cuadrupolar. Si tengo una interacción cuadrupolar. ¿Por qué? Porque el spin del nitrógeno es spin 1. Depende del tipo de sistemas que yo estoy rodeado, voy a tener diferentes interacciones. Voy a tener también una anisotropía en el acoplamiento escalar y así sucesivamente. Entonces yo voy a tener el acoplamiento dipolar, yo voy a estar hablando del apantallamiento. Ese apantallamiento, además, la parte isotrópica me interesa que se sume o se reste al acoplamiento Zeeman para poder yo ver el desplazamiento químico, no lo puedo desaparecer. El acoplamiento cuadrupolar, también vamos a hablar brevemente de él, y el acoplamiento J y su anisotropía. ¿Okay? Entonces, todas estas contribuciones están en un sólido o en un líquido. Ahora, ¿por qué no me preocupo en un líquido? Porque en un líquido pasan dos cosas. Primera, al tener dilución, la distancia promedio que yo tengo entre una molécula y otra aumenta y se vuelve muy grande. Puede ser del orden de 10 Armstrongs, 15 Armstrongs, depende de la disolución, la distancia promedio entre moléculas. A esas distancias, lo que es el acoplamiento, las interacciones dipolares prácticamente están minimizadas entre moléculas y solo voy a ver las interacciones dipolares al interior de la molécula. Al pasar eso, yo puedo tener espectros como el NOESI, que me permiten ver esas interacciones dipolares dentro de las moléculas y me permiten ver configuraciones en solución. Pero en el sólido, yo voy a ver esos efectos tanto dentro de la molécula como con otras moléculas. Por otro lado, cuando yo estoy hablando de soluciones, yo tengo que las moléculas, como les mencionaba, están girando muy rápidamente. Y esto va a depender un poco del tamaño de la molécula. Moléculas pequeñas giran muy rápido y por lo tanto, en promedio las voy a estar viendo como esferas. ¿Qué pasa con los polímeros? Los polímeros que yo logro disolver generalmente me dan espectros muy feos. Sí, ¿verdad? Ya estoy viendo que muchos tienen ese problema. Bueno, eso es parte normal, digamos que es la característica de salí feo, así soy. Entonces, pues sí, y al hacer así, en solución, me dan muy poca información. ¿Por qué? Porque se mueven despacio. Y al moverse despacio, empiezan a no ser esferas dentro de lo que es el desplazamiento químico y empiezo a tener que no me da lo mismo tener un desplazamiento químico para un benceno que está así, que otro que se está moviendo tantito más acá, y entonces se me empiezan a hacer anchas las señales. ¿Okay? Y eso de señales anchas pues es normal en un polímero. En solución, ¿podremos en sólidos mejorar eso y entonces tener mejor resolución? Y es una de las cosas que esta técnica ayuda muchísimo. Ok. Del acoplamiento cuadrupolar y del acoplamiento J voy a hablar muy poco también durante esta plática, pero son acoplamientos que existen y que también, dependiendo de la movilidad de la molécula, pueden tener efectos que me complican la existencia cuando yo estoy hablando de sólidos. Ok, entonces quedamos. La energía de Zeeman es la básica, es el principio básico de resonancia magnética nuclear. Yo tengo aquí, pues simplemente que para un campo magnético dado, una diferencia de energía entre mis dos niveles, para cuando yo estoy hablando de spin 1 medio, tengo dos componentes y la condición de resonancia se va a dar cuando la energía de la radiofrecuencia que yo esté aplicando, pues sea igual a la energía que me separan estos dos sistemas. Eso es, digamos, la clase de resonancia en analítica, no sé cuál, la 1 o la 2, o en análisis instrumental básico. Lo que es importante aquí es lo siguiente. Yo tengo que la energía de Zeeman va a depender tanto del campo magnético externo como de esta constante que está allí, que es la constante giromagnética. Y esa constante giromagnética le hacemos poco caso en solución. Simplemente de repente nos preocupamos un poquito porque esa constante giromagnética sabemos que es 4 veces más grande para protón que para carbono, ¿sí? Y eso básicamente es lo importante para poder hacer experimentos de INEP, de depth y hablar un poco de sensibilidad. Pero realmente, ¿qué es lo que me está diciendo? Lo que me está diciendo es que mientras más pequeña sea, este desdoblamiento es más pequeño. Y mientras más pequeño es ese desdoblamiento, menos sensibles son mis núcleos. Esa es la parte importante. Y entonces, si yo quiero, por ejemplo, hacer nitrógeno 15, que tiene una constante giromagnética muy chiquita, pues tengo problemas de sensibilidad. Y por lo tanto, en solución, me veo obligado a enriquecer la muestra en nitrógeno 15, lo cual me aumenta mucho los costos. ¿Se podrá en sólidos hacer espectros de resonancia nitrógeno 15 sin necesidad de enriquecer la muestra? Entonces aquí vamos a ver ya en la segunda plática que eso es posible. Ok, entonces vamos a empezar hablando de lo que es el acoplamiento dipolar heteronuclear. Y los nombrecitos a veces son muy complicados y parte de la idea que me pidieron que les ayudara aquí es ir entendiendo esto, primero en español para que después en inglés no suene a trabalenguas. ¿Qué es el acoplamiento heteronuclear? Pues el acoplamiento heteronuclear quiere decir entre núcleos diferentes, pero ¿cuáles núcleos? Entonces aquí la clave es pensar que yo tengo un núcleo abundante que es protón, ¿sí?, que se va a estar acoplando con mi núcleo poco sensible, que es el que voy a estar viendo por lo general. O sea, en sólidos yo por lo general las técnicas más comunes y corrientes es ver núcleos poco sensibles, no se acostumbra a ver mucho protón, para protón se necesitan técnicas un poco especiales, pero si entienden esto vamos a ir entendiendo después que pasarnos a protón tampoco va a ser mucho problema. Ok, entonces en un sólido yo tengo núcleos insensibles que pueden ser carbono y sensibles que puede ser protón, respectivamente. También un núcleo insensible podría ser nitrógeno. En algunos casos incluso yo podría pensar en núcleos insensibles como fósforo, que fósforo tiene una constante giromagnética un poquito más grande, pero los voy a seguir considerando como sensibles e insensibles, es decir, los núcleos sensibles básicamente voy a estar hablando de protón y de flúor, ¿sí?, los núcleos que están en la banda alta. ¿Okay? Pero bueno, ahora, algo que es cierto, siempre ambos núcleos se me orientan en el campo. Yo estoy viendo carbono y a lo mejor me olvidé de protón, pero protón está magnéticamente también jugando en el sistema. Y bueno, en un sólido, estos núcleos pueden estar a distancias menores de 10 Armstrongs y eso empieza a ser un problema. Y cuando estoy diciendo 10 Armstrongs, menores a 10 Armstrongs, estoy hablando entre moléculas diferentes o dentro de la misma molécula, sistemas que normalmente a lo mejor en una solución se me desenrolla una proteína o se me desenrolla un polímero y no estarían cerca. Y aquí van a estar cerca. Y en ese momento, ¿qué es lo que va a pasar? Pues que este campo local, que es el que me da el desplazamiento químico, por cierto, ¿sí?, para el núcleo insensible se afecta por el núcleo sensible y viceversa. ¿Okay? O sea, la dirección es en los dos sentidos. Y la ecuación, y alguien me estaba diciendo, no, es que tiene muchas ecuaciones tu presentación. No se preocupen, estas ecuaciones son importantes para entender el fenómeno, pero no los vamos a deducir. Los físicos ya nos hicieron el favor de hacer esto bien por nosotros y la mayor parte de nosotros que estudiamos o materiales o química o biología, pues lo que nos interesa es entender qué hicieron para poderlo utilizar. Y entonces veamos esta ecuación. ¿Qué me dice La contribución a la energía para el acoplamiento heteronuclear, ¿de qué depende? Bueno, primero que nada depende de las constantes giromagnéticas. Mientras más grande sean las constantes giromagnéticas, más grande es la interacción heteronuclear. Es decir, no es lo mismo trabajar, o no va a ser lo mismo el efecto que me genere el estar estudiando un espectro donde tengo fósforo que está interaccionando con protones, en donde estas constantes ambas son grandes, a tener una en donde tengo protones y tengo carbono, o más aún, tengo un nitrógeno. Si yo tengo nitrógeno, esta interacción es menos importante que si tengo carbono o que si tengo fósforo. La otra cuestión que veo es que esta interacción depende inversamente del cubo de la distancia, es decir, decae razonablemente rápido. Lo cual me quiere decir que a distancias de alrededor de 10, 15 angstroms, prácticamente esta interacción ya la puedo despreciar, ¿sí? Pero a distancias menores no. Después tengo aquí este numerito raro, 3 coseno cuadrado de teta menos 1, que lo que me está diciendo es, este ángulo es el ángulo que yo tengo, o es el ángulo que se forma entre el vector que me une los dos núcleos, y ojo, dije vector, no enlace. O sea, yo puedo estar hablando de un vector que me une dos núcleos que están razonablemente cerca, pero que no están enlazados químicamente. ¿Okay? Y ese vector, ¿qué ángulo me está formando con el campo magnético externo? ¿Okay? Ahora, si yo les digo, ahora imagínense, pónganse a pensar ahí en su cabecita un poco. Yo tengo 10 a la 20 moléculas que apachurro y aprieto y meto en un tubito de resonancia de sólidos. ¿Cuántas orientaciones voy a tener? ¿Cuántos ángulos teta voy a tener? Pues todos los que se imaginen, o sea, todos los que se imaginen, es decir, ¿cuántos valores de energía voy a tener? Muchos. ¿Qué me ocasiona eso? Pues que si yo no me elimino esto, en lugar de tener una señal delgada, fina para un núcleo determinado, voy a tener una señal ancha. ¿Sí? Entonces yo lo primero que tengo es sólidos. Si no tengo bien hecho el sistema, si no tengo bien caracterizado y bien fijadas las condiciones de estudio, mis señales van a ser anchas y poco resueltas. Ahora, la otra cuestión es aquí. También depende del producto de la componente en la dirección Z del momento magnético y del átomo insensible por el campo magnético en la dirección Z, por la componente en la dirección Z del momento magnético del núcleo sensible. ¿Ok? Bien, ¿esto qué quiere decir? Todo esto. Bueno, quiere decir que valores, la energía o los valores de esta interacción están en el orden de los 30 kilohertz. Fíjense, en un equipo de 300 megahertz, yo tengo que la energía del desdoblamiento Siemens es del orden de 10 a la menos 20 joules por mol. ¿Okay? Y este es de 30 kilohertz, es decir, es 1000 veces menor. Estamos hablando de una contribución de 10 a la menos 23 joules por mol. Y sin embargo, esto me da una dispersión que para un equipo de 300 megahertz estamos hablando de 30.000, de unas 100 partes por millón. ¿Sí? O sea que si yo estuviera viendo una señal como sería la del benceno o la de un metilo y tuviera este tipo de interacciones, el ancho de banda de cada una de ellas sería del orden de 100 partes por millón. ¿Sí? Es decir, si yo tengo tolueno, ¿qué es lo que pasaría? Yo no vería la señal de benceno y no vería la señal del metilo. ¿Por qué? Porque en esas 100 partes por millón estarían tapadas una con otra. Estaría viendo una señal muy ancha. ¿De acuerdo? Ok. Ahora, cuando yo tengo ese desacoplamiento dipolar heteronuclear, ¿qué es lo que puedo hacer? Pues lo primero que me dirían, desacopla, igualito que lo haría en solución. O sea, si yo puedo desacoplar en solución, ¿por qué no puedo desacoplar en sólidos? Y cuando yo tengo esto, lo que yo voy a hacer es, o lo que vamos a decir es lo siguiente. Cuando yo tengo, esta es la secuencia básica, prácticamente cualquier experimento en sólidos, y lo que yo voy a querer es que esta energía valga cero. O sea, yo quiero deshacerme de todas las interacciones dipolares heteronucleares que me hagan ancha la banda la señal, ¿sí? O sea, si yo puedo deshacerme de estas 100 partes por millón y volverlas un ancho de banda de una parte por millón, más o menos voy a tener un espectro de muy buena resolución. ¿Cómo logro eso? Pues igual que en solución, yo voy a hacer un desacoplamiento. Y ese desacoplamiento que está aquí marcado, si se fijan, a diferencia de solución, mantengo apagado aquí el sistema. Esto no hay tiempo en esta plática de verlo en detalle, pero tiene que ver con cuestiones técnicas por un lado y por otro con cuestiones de ya el uso de la técnica más elaborada. Diferencia, en solución yo tengo mis concentraciones del analito que va en el orden de 10 a la menos 3, 10 a la menos 2. Y cuando abusa algún estudiante me estoy yendo hasta 10 a la menos 4, 10 a la menos 5. ¿Sí? Cuando yo tengo una solución 10 a la menos 3 molar, 10 a la menos 2 molar, pues la cantidad de potencia que necesito para atarantar a todos los protones al estar desacoplándolos es poca. Estoy hablando de unos 30 watts, cuando mucho. Sí, así, cuando mucho. 30 watts de potencia, pues imagínense, piensen en los focos, pues es un foco con el cual apenas uno ve. En cambio, cuando yo tengo un sólido, la cantidad de protones que tengo por unidad de volumen aumenta muchísimo de la muestra. ¿Okay? Entonces quiere decir que yo necesito darle más potencia a mi sistema. Y una de las diferencias importantes en los equipos de resonancia magnética nuclear es aquellos que solo son para sólidos, que solo son para solución, utilizan fuentes de poder que van cuando mucho hasta 100 watts. Y dice uno, 100 watts ya es bastante. Para tener un equipo de sólidos que funcione razonablemente bien, lo primero que tengo que fijarme es que ese equipo tenga una fuente de poder de por lo menos 300 watts. Y si yo puedo comprarle a ese un accesorio que me dé 1 kilowatt de potencia, mejor. Entonces, ¿qué es lo que vamos a hacer? Pues vamos a hacer lo mismo, vamos a hacer un desacoplamiento en donde lo que voy a hacer es que esta componente se convierta en cero. Y bueno, dentro del álgebra elemental que todos nosotros sabemos que 0 multiplicado por lo que sea me da 0. Entonces con eso aniquilo este sistema. Entonces me basta con tener un desacoplamiento, es decir, irradiar con alta potencia mi muestra en la frecuencia de resonancia del núcleo sensible para que yo pueda ver el núcleo insensible sin esta interacción dipolar. Sí, esa es la primera cosa que tenemos que tener clara. Y bueno, al ratito vamos a volver a ver esta función, pero en un momento determinado, incluso yo podría decir, ya lo logré, ya tengo 0. Ahora lo que sería muy interesante, y estos son cosas que les van a platicar más adelante también los profesores, es a mí me gustaría ahora reconstituir y ver esta interacción dipolar, pero solo para ciertos núcleos. Y entonces lo que yo tendría que hacer es hacer que este valor de S deje de ser 0, pero de manera selectiva, ¿okay? Para ciertas frecuencias. Y entonces esto sería un reacoplamiento dipolar. ¿De acuerdo? Bien, vamos a ver lo que sigue. Siguiente, ya hemos estado empezando a introducirnos en esto de la anisotropía del desplazamiento químico. Para mí el ejemplo clásico y bonito es el benceno, o sea, un benceno en solución se está moviendo tan aprisa que yo lo vería como una esfera, grande pero sería una esfera. En el momento en que yo lo congelo, que yo lo solidifico, yo voy a tener capas. De hecho, si lo logro cristalizar, el benceno cristaliza formando una especie de apilamiento. ¿Okay? Entonces, si yo tuviera ese cristal y lo pusiera dentro del equipo de resonancia, lo orientara y después fuera variando el ángulo, lo que yo estaría viendo es que el desplazamiento químico se me estaría moviendo. ¿Okay? ¿Por qué? Porque el sistema no tiene la propiedad de ser una esfera, sino más bien tendría la propiedad de ser una elipse. ¿Okay? De hecho, hay experimentos en resonancia magnética nuclear de sólidos que lo que puedo hacer es un cristal, orientarlo dentro del equipo y estar viendo cómo es el espectro de resonancia magnética nuclear en función del ángulo que yo tengo o de la orientación que yo estoy trabajando. Y esto, en términos de materiales, me puede dar muchísima información. Pero bueno, veamos aquí qué es lo que es importante. O sea, cuando yo hablo de anisotropía, lo que estoy diciendo es, yo voy a tener sistemas que no van a tener la misma magnitud de lo que quieran, apantallamiento, ¿sí? En una dirección que en otra. O si no le quieren decir apantallamiento, le podemos decir densidad electrónica. ¿Sí? La densidad electrónica no es homogénea en diferentes direcciones. Y bueno, esta distribución electrónica, por lo general, es no esférica. Y por lo tanto, yo voy a tener que esta molécula tenga dependencia de la orientación de la molécula. Insisto, cuando yo tengo en solución una molécula pequeña, se mueve tan aprisa que esta pelotita la termino viendo como una esfera. Ok, y ahora, ¿qué pasa con...? Ay, no sé si alcanzan a ver las ecuaciones, espero que sí. La anisotropía del desplazamiento químico, ¿ahora de qué depende? Pues también tengo ahí una energía y depende de la constante giromagnética del núcleo, del campo magnético. Obviamente aquí se empieza a ver, es por eso que nos interesa tener campos magnéticos grandes, porque yo voy a tener una mejor contribución a ese desplazamiento químico mientras más campos magnéticos, mientras más alto sea el campo magnético. Pero empiezo a tener un problema. Yo voy a tener un desplazamiento isotrópico, el que conocemos, ¿sí? El cloroformo aparece a 7.26 partes por millón y me lo sé bien y ahí está, sí, en solución. Si yo lo tengo en sólido, voy a tener ese valor más un medio del valor de la anisotropía por, otra vez, 3 coseno cuadrado de teta menos 1. ¿Okay? ¿Esto qué es lo que me está diciendo? Que si yo congelo cloroformo y lo meto dentro de la resonancia, obviamente no voy a tener una esfera, voy a tener una especie como de pera. ¿Okay? Y esa pera puede estar orientada en muy diferentes orientaciones. Y eso me va a generar que el carbono que yo voy a estar viendo va a tener diferentes valores de desplazamiento químico, al final de cuentas. Ok, ¿y esto qué me da? Bueno, un poco lo que vamos a ver es que este desplazamiento isotrópico, pues al final de cuentas es la suma de las diferentes componentes promediadas. Y esto que está aquí es finalmente la diagonal del tensor, la divido entre 3 y es esto. Y el tamaño, o sea, a ver, si yo pienso en el cloroformo como una molécula poco simétrica, poco anisotrópica, y la comparo con la del benceno y pienso en el carbono, claramente el carbono va a tener mayor anisotropía, porque no es lo mismo tener un protón en un orbital sp3 contra un cloro en un orbital sp3, contra tener sistemas en donde yo tengo un sistema sp2 y un orbital p deslocalizado, pero es muy diferente en una dirección que en la otra. Entonces la anisotropía es muy distinta. El cloroformo va a tener forma de pera, el benceno tiene forma de plato. ¿Sí se van dando cuenta de la idea? Entonces eso me dice, por allí tengo que tener una medida del tamaño. ¿Cuál es ese tamaño? Bueno, ese tamaño está aquí como la medida de la magnitud del desplazamiento, de la anisotropía en el desplazamiento químico, y es un medio de estas cosas. Y por convención simplemente, generalmente ustedes van a ver reportados que este tensor se va dando en orden de cómo van apareciendo las frecuencias. ¿Okay? Ahora, ¿de qué tamaño estamos hablando esto? ¿Se acuerdan? La interacción heteronuclear era del orden de 100 partes por millón, ¿verdad? ¿Sí? Bueno, pues esta sigue siendo de ese mismo vuelo. Estamos hablando de 100 partes por millón. Es decir, si no me deshago de esta anisotropía, también voy a tener un problema de un ancho de banda muy grande. Y bueno, en este caso, perdón, es del orden, sí, 120 partes por millón para carbono 13. Ok, otro que van a ver en detalle ustedes durante el curso es el acoplamiento homonuclear, que les digo, no es importante en carbono 13, pero si yo tengo un sistema en donde estoy trabajando materiales derivados de fósforo, como podría ser por ejemplo hidroxiapatita. En la hidroxiapatita yo tengo mucho fósforo y a muchos de nosotros nos interesa la hidroxiapatita. ¿Por qué? Porque es un material que tiene interés en biomedicina. ¿Por qué? Porque me gusta hacer prótesis, por ejemplo, o hueso artificial. Sí, nada más que para estudiarlo, me gustaría estudiar fósforo, pero entonces ahora resulta ser que tengo alta concentración de fósforo. Y en el momento en que yo tengo alta concentración de fósforo, este acoplamiento homonuclear se encuentra presente. Y ese sí me va a dar un poquito de lata. Ese acoplamiento homonuclear también depende como 1 entre R al cubo, depende del cuadrado de la constante giromagnética, lo cual quiere decir, mientras más grande la constante giromagnética, más me va a afectar. Y esto se vuelve una pesadilla para para protón, por ejemplo. Y después tengo algo que acá se me empieza a complicar más, porque tengo también nuevamente el 3 coseno cuadrado de teta menos 1, pero acá tengo que sí es igual al producto de las componentes en la dirección Z de los átomos que están interaccionando, pero también es igual al producto escalar de los dos vectores, y eso me genera una complicación técnica. Ya desde el punto de vista de cuántica, los que por aquí les guste, saben que esto me complica un poquito el cálculo. Pero desde el punto de vista técnico, me implica que si esto es importante, no necesariamente voy a hacer que esto valga cero. ¿Ok? Y nuevamente también quiero hacerlo cero. Ahora, la ventaja para interacciones como carbono-carbono es pequeña, es del orden de 5 kHz. Sí, 5 kHz, pues bueno, está bien, nada más son 50 partes por millón. Sí, pero 50 partes por millón siguen siendo demasiadas para tener un espectro de alta resolución. Entonces, ¿qué es lo que vamos a hacer? Bueno, antes de ver cómo le vamos a hacer, una cosa que yo quiero también que vean es que el acoplamiento cuadrupolar, es decir, y este sí es importante, yo de repente quiero estar estudiando compuestos biológicos, aminoácidos, proteínas, y pues por ahí una de las cosas más importantes que hay es el enlace peptídico. Y en el enlace peptídico yo tengo un enlace carbono-nitrógeno, pero fíjate que nitrógeno normal es nitrógeno 14 y eso tiene spin spin igual a 1, y por lo tanto resulta ser que voy a tener la presencia de un acoplamiento cuadrupolar. ¿Sí? Y ese acoplamiento cuadrupolar pues me puede dar un poco de lata. Y aquí, aunque lo estoy representando de una manera diferente porque ya es el desdoblamiento, el desplazamiento, este desplazamiento depende del tamaño de ese acoplamiento cuadrupolar. Cuando se me acoplan demasiado, yo voy a poder ver que, por ejemplo, ese carbonilo del enlace peptídico, que yo debería esperarlo ver como un cingulete, se me desdoble. Y en el desdoblamiento yo esté teniendo este resultado. Y entonces la interpretación se vuelve un poquito más complicada. ¿Por qué? Porque yo tengo que saber si lo que estoy viendo es un desdoblamiento o es una impureza, o tengo dos carbonilos. ¿Sí? Ahí es en donde van a entrar la práctica de cada uno de nosotros. Ok, nuevamente esto también depende de R al cubo. Cuando estoy hablando, como en el ejemplo que les hablé, en este momento, un enlace peptídico, esa R es muy pequeña. Estamos hablando de 1.4, 1.3 Armstrongs de distancia. Pero también yo puedo tener esta interacción a través del espacio. Acuérdense que esto vuelve a ser importante. Y esto empezará a ser despreciable cuando R sea mayor de 10. Ok. Y ahora, la última. Yo voy a tener que también puedo tener en el acoplamiento escalar J cierta anisotropía. Es decir, que de repente yo diga, ay, a lo mejor alcanzo a ver un tripletito por allí de, ¿qué les gusta? Un fósforo unido a un carbono. Se pueden acoplar. Entonces, yo estoy viendo el carbono y de repente veo que se está acoplando con el fósforo. Pero una de las cosas que me voy a dar cuenta es que el valor de J para un lado o para el otro del triplete que estoy viendo no es el mismo. ¿Sí? Y esto se debe a que yo voy a tener una anisotropía en el acoplamiento escalar, en donde también está aquí la magnitud del acoplamiento escalar, dos ángulos que dependen de la orientación en el campo magnético y cómo están los ángulos entre ellos. Y es poco frecuente ver este tipo de acoplamientos, pero se llegan a observar. Bien, ¿cómo le hago? ¿Cómo le hago para deshacerme de esto? Entonces ya vimos hace un minuto que lo que podemos hacer primero que nada es desacoplamiento con alta potencia. Esa es la primera cuestión importante. Pero a veces eso no es suficiente. Y si yo me quiero deshacer de la anisotropía en el desplazamiento químico, y si yo me quiero deshacer o ayudar a deshacerme del acoplamiento heteronuclear, lo que podría hacer es hacer que esta parte de las ecuaciones que tenía, 3 coseno cuadrado de teta menos 1, lo hiciera cero. Si yo hago cero eso, nuevamente cero multiplicado por lo que sea, me desaparecen todas las contribuciones. Y entonces, a final de cuentas, lo que vamos a hacer es poner a esta muestra que de alguna manera tenía cierta anisotropía a girar rápidamente en un eje, ¿sí? De tal manera que solo las contribuciones que me van a estar proyectándose en esta dirección tengan valor, ¿ok? Pero si yo empiezo a variar este ángulo de la muestra de tal manera que esto lo convierta en cero, en el momento en que yo esté girando aquí, promediando por velocidad a la muestra, lo que voy a hacer es que promedio a cero todo el vector que estaría, todos los vectores, todas las orientaciones de los vectores en este plano, y solo me quedo con este vector y su componente aquí. Y si eso hago que 3 coseno cuadrado de teta menos 1 sea igual a 0, lo colapso y desaparezco todas las interacciones. ¿Y eso cómo se hace? Bueno, fíjense, ¿qué es lo que vamos a hacer? En el acoplamiento heteronuclear hice que S valiera 0 por el desacoplamiento heteronuclear de alta potencia, y al mismo tiempo hago que este valor sea 0. Si estos dos valores son 0 o muy cercanos a 0, prácticamente hago que esta energía desaparezca de mi espectro, ¿ok? Lo desaparezco, y es como si estuviera ya en solución. Después, en este otro caso, cuando es homonuclear, yo puedo incluso también solo con poner en ese ángulo mágico a mi muestra, hacer que valga 0 el sistema. Y finalmente, en el desplazamiento químico, si yo este sistema lo hago 0, me quedo con el desplazamiento isotrópico, ¿sí? Y entonces estoy logrando lo que queríamos, tener las condiciones en donde yo a un sólido lo voy a ver como si lo tuviera en solución, ¿sí? Es decir, simulé las condiciones de una molécula en solución, la puse a girar rápido y desacoplé totalmente. Bien, el experimento básico de sólidos tiene como característica lo siguiente: se conoce como más o girar al ángulo mágico, y para eso se utilizan cosas. Aquí ya un poco lo que quiero es que vayan viendo las componentes. O sea, hace rato les presenté el dibujito, les presenté los dibujos de los rotores, y lo que voy a hacer es poner ese rotor a girar a 54.44 grados. Y un ejemplo, si yo veo este sistema girando y sin girar con el desacoplamiento de alta potencia, paso de esto, en donde tengo 300 partes por millón de ancho de banda, ¿sí? O sea, imagínense 300 partes por millón, para aquellos que usan carbono, es como una línea recta en la parte de arriba del espectro, o sea, no veríamos nada. Cuando yo hago este experimento, paso de este sistema a este tipo de espectro, un espectro de alta resolución, ¿okay? ¿Cómo logro eso? Con este tipo de rotor, de stators, que es en donde se pone la muestra aquí adentro, ahí está la bobinita, y a través de neumática, es decir, de aire comprimido, pongo a flotar la muestra, el rotor, y a girar. Y bien, este experimento tiene un problema, es poco sensible, y al ser poco sensible me pasa lo que en carbono. Un experimento en carbono poco sensible implica algo: tiempo, y en este equipo y en este tipo de tecnología, tiempo es dinero, ¿sí? Cuesta mucho este tipo de experimentos. Entonces, en solución tenemos experimentos como el DEPT y el INEPT, que me hacen lo que se conoce como transferencia de polarización, ¿sí? Y en donde un espectro lo puedo reducir en un 25% el tiempo de adquisición, ¿sí? Es decir, un experimento que me duraba 2 horas, con media hora de experimentación tengo un buen espectro. Obviamente hay costos siempre en esto, ¿no? Pero, en fin. Y bueno, el concepto básico de transferencia y polarización en solución está básicamente aquí, en generar un pulso simultáneo entre el núcleo sensible y el núcleo insensible, de tal manera de transferir la magnetización de un núcleo al otro, ¿okay? Es básicamente la idea esencial. ¿Y esto qué es lo que me va a generar? Que yo también tenga el equivalente en sólidos. En sólidos se le llama ligeramente diferente, se le llama polarización cruzada, y en donde yo lo que voy a hacer es polarizar a los protones y después, a partir de un pulso simultáneo, que se conoce como polarización cruzada, transferir esa magnetización que tenía el protón a los carbono. Y para esto lo que se hace es que se tiene que cumplir una condición que se le conoce como la condición de Harman-Hahn, en donde lo que estoy diciendo es que la frecuencia a la que procesan mis núcleos una vez que caen al plano XY tienen que ser igual para el núcleo insensible que para el núcleo sensible. ¿Sí? Si yo logro eso, voy a tener una buena transferencia de magnetización, y si yo tengo esto, voy a incrementar dramáticamente la sensibilidad de mis experimentos. Esto, digamos que es así un panorama muy rápido. Espero que después lo van a ir viendo en detalle ya con los profesores, y si tienen alguna duda, estoy para servirles.
Sí, tendríamos tiempo para una preguntita así rápida, si alguien tiene alguna inquietud. Sí, allá, por favor.
No, de hecho, en sólidos relajan más rápido que en solución. Por lo mismo, por estas interacciones dipolares, tú tienes una manera de dispersar muchísimo más rápido el spin. Cuando tienes materiales que no tienen muchos protones, por ejemplo, entonces sí los tiempos de relajación se vuelven difíciles. Por ejemplo, silicatos. O sea, a mí me ha tocado trabajar con algunos cuarzos o materiales de silicio, en donde los tiempos de relajación se me han ido a 60 minutos. Así. Y obviamente es un experimento carísimo, porque pues, tienes el equipo muerto ahí por horas. Pero en general, los tiempos de relajación son menores cuando tienes protones. ¿Sí? Y obviamente, si estamos hablando de materiales, te pueden pasar muchas cosas. O sea, una zeolita, una tierra, va a relajar rapidísimo. ¿Por qué? Porque siempre vienen con impurezas de fierro, por ejemplo. Entonces, los tiempos de relajación van mucho más para allá.
Muy bien, pues le agradecemos al doctor Mendoza su interesante participación. Espero que los haya puesto al tanto en la técnica y que las siguientes conferencias sea más fácil digerir los comentarios. Algo que se omitía, el doctor Guillermo Mendoza, pues actualmente se ha movido a la Universidad de Guanajuato, Campus León, y pues cualquier pregunta que tengan después de esta plática, pero la pueden hacer con toda la confianza del mundo. Le agradecemos mucho al doctor Mendoza su presencia. Gracias. Well, I'm glad to introduce our next speaker, Professor Taulel. You can come here, please. Who is currently working at the University of Versailles and Canton, France. I'm going to give you some details of his academic record. He got 2 Master in Science degree in Analytical Chemistry and in Physical Chemistry, both from the University of Pierre and Marie Curie. He got his PhD degree in Analytical Chemistry from the same university. He was director of the NMR on Solid State Chemistry Laboratory at the University Louis Pasteur in Strasbourg. And also he was research director first class at the Chemistry Department of the French National Center for Scientific Research. Currently, he's director of Tectospin, the solid-state NMR group of the Institut Lavoisier at the University of Versailles. He has more than 150 papers and 2 patents in high-temperature NMR probe design, and he has 80 conferences after the ones, 81. His main research topics are in spectroscopy of ionic liquids, solid-state NMR spectroscopy and instrumentation, nanoporous inorganic materials elaboration and characterization by solid-state NMR, crystallogenesis of inorganic compounds by in situ NMR, and NMR crystallography polymorphisms characterization of pharmaceutical materials. He was awarded with the French Science Academy Prize, Paul Pascal. So you're very welcome. Thanks a lot for coming, and you have this auditorium for you.
Thank you very much for this very kind presentation, and I will probably need 1 minute to set up my computer in order to present my talk. It's okay, everything? Yeah, sounds to be okay. Buenos días a todos. I'm not going to talk in Spanish. I would have loved. But I'm really too slow. I can understand, but and then you can ask also questions in Spanish. That's no problem. Actually, I'm very glad to be here. And as you know, it is always a pleasure to be in a family and sharing things in a very nice atmosphere. So as this can be represented by the painting here, science like love. Increases when it is shared. So this is exactly what I mean to be here, is just to share. And I'm pretty sure that by sharing, it goes in both directions, from you to me, and I hope a little bit from me to you. So my group is working in Versailles University, close to the palace. The university is not located in the palace. Hopefully for us, because the bill for heating the building is much too high. So this is the reason why we're located a little bit further away from the palace. What do I want to show about solids and NMR? Actually, solids can represent different states of matter. You may have shells in water. You may have rocks with petrol in them. You may have zeolite that look like crystal that are closed, but actually this is an inner surface that is absolutely tremendous. You may have foils with polymers and metals. You may have proteins. You may have different type of nanoscience, nanoparticles that you can form on surfaces. You may have many sponges-like, and those objects, all of them are called solid. What do you need to do solid-state NMR? Very few things, actually. You need to have a magnet. It's a very expensive piece of equipment. And you need to have a coil. Why? Because you are having magnetic moments that are immediately aligned in the magnetic field that you apply onto them. So this is the first condition. They are all aligned like a guitar string. Now the question is, if you want to hear the sound of an atom, or hear the sound of a guitar string, you have to do something. You have to pinch it. The way to pinch it is just to generate a variable magnetic field that will change the orientation of the magnetic field. However, there is a considerable difference between the magnetic field here that is extremely homogeneous, 10 to the minus 9, 10 to the minus 10 variation in space and in time. So this is the very stable homogeneous magnet. And in a coil, this is not the same story actually. When you apply a current to a coil, what you have along the coil axis is a variation of the magnetic field, radio frequency magnetic field that is very important. So for all the rest of the talk, you have to remember that those two magnetic fields do not behave the same at all. And so we have to keep that in mind. Now, when NMR was discovered, it was discovered by just measuring the voltage that you obtain after applying a pulse or a current to the coil. And when you stop applying the current, then you are generating with a variable magnetic moment a voltage at the coil ends. So this is what Felix Bloch has presented and then has designed equations, the equation of motion of that magnetic moment. Actually, this is a piece of history of science that at the same time, Pound and Purcell were using a quantum mechanic description for it. And actually, something that is even weirder is that even today, most of us NMR spectroscopists are using both representation, the macroscopic magnetic moment that generates the voltage in the coil, and the microscopic nuclei level, where you are having isolated magnetic moment and you generate or you represent phenomena by a quantum mechanical fashion. I am not going to redo what my colleague has so well done just before me, presenting all the interaction taking place in a sample. What you have to know is that NMR is one of the techniques where the difference between levels, between energy levels, is the lowest. So actually you are having not one dominant interaction that generate your spectrum, but you're having many of them. And this is in a way the difficulty and the strength of NMR spectroscopy in general. So if I come back now to Hamiltonians, I'm going to talk about quantum mechanics. I'm telling you that you know a lot about quantum mechanics. Usually you don't know you know. So actually here, in order to go through all the technology of solid-state NMR, you have to reduce the complexity by using some notations that are making your life really simple. If you don't do that, then it's really a nightmare. So look at the different type of interactions that you're having. They've been listed just before me. And what you look here is that actually every time you're looking at an energy level or something that will define the energy level, then what you see is that there is a part that is due to the magnetic moment, a part that is due to the orientation of your sample in space, and the part that is a scaling number. If you are measuring energy in units, then you have to relate the two first dimensionless part with a scaling factor. So this is what you have. And this is a small list of interaction that you may have in a sample. Chemical shift anisotropy, dipolar homonuclear coupling, dipolar heteronuclear coupling, scalar heteronuclear coupling, quadrupolar interactions. So if you look at two aspects among those Hamiltonians, there are numbers here that are not having any space part and any magnetic part. Any space part. So they do not depend on the orientation. So the magnetic part remains. And then you recognize something that you are used to. This is liquid state NMR. When your molecule is moving statistically and experiencing every sort of orientation, at the end, the Hamiltonian is an average Hamiltonian by the motion. And so you're left with just a number that is multiplied by the magnetic part. So in a way, you see that you do a lot of things in high resolution liquid state NMR by using only two small parts of the Hamiltonians that you're having there. So it means by just reading the position of a line and the multiplicity of coupling, you can extract from a molecule many aspects about the structure. Now, let's go into a little bit more details. If I take just one part, the dipolar part, why the dipolar part? Because this is playing a critical role in solid state NMR. So you have seen that there's a part here, a scaling number, the coupling factor, and a magnetic part. So this is where the quantum mechanics starts. Why do we have such expression for energy, for Hamiltonian? Actually, what you know already is that if you're trying to represent atoms by a nucleus and an electron, this is the hydrogen atom model. What you have is just surfaces that we call usually orbitals, and those orbitals represent the so-called probability of presence of electron. Actually, now, this is an unfortunate denomination. Why? Because actually, what do you have when you solve the Schrödinger equation? You are having just attraction and repulsion of electrostatic forces. So when you're dealing with the presence, the probability presence of an electron, actually you're defining an energy that is having the same, you're describing a surface that is having the same energy on all the points of the surface. Every time you're going to deal with interactions, each of this interaction will be described by surfaces of equal energy. This is exactly what we will have for the rest of the discussion. Every time we are dealing with a new interaction in NMR, you don't have to worry that much about the fact that you're going to have a different type of surface, because they will be always the same. They will have always the same shape, but they will differ by the scaling number and by the magnetic part. Where are those shapes coming from? Actually, this was solved at the end of the 18th century, and those are called the polynomial Legendre, and they are defining surfaces. Take a surface of an arbitrary shape. How can you decompose a surface into a series of discrete surfaces that will be a basis, so for describing another surface? What is a basis in this case? A basis means that you're making surfaces, but you cannot describe one surface by another. They are orthogonal. This is what are the polynomial Legendre. They are defining orthogonal surfaces. So every time you're having a surface of arbitrary shape, then you can always decompose them in one single unique series of surfaces. This is exactly what we do with orbitals. So we are going to do exactly the same thing with any interaction in NMR, and I'll show you, and I will recall some of the principles that allow you to understand the relation between writing a Hamiltonian and dealing with an experiment. you have to write energy levels. Let's start by one Hamiltonian. You have a space part, a spin part, and then a scaling number. Here, this part, which is the chemical shift, can be divided in two parts. This one, and its magnetic part, and this part. Okay, now let's calculate an energy. Having a spin state of 1/2, what is that? This is just the orientation of your magnetic moment. It's a line or counter a line. So this is a state, a pure state. So when you write energy levels, you write that. You want to obtain what is the effect on a system that has a given energy and that is oriented towards the constraint. Thank you. Okay. I'm not a singer. I don't know how to swallow those things. Anyhow, when you do that, then obviously what you are having is just a system that is represented by an interaction, and this interaction is represented by a surface of energy. So now you are having a magnetic moment, and you say, this magnetic moment in this context, how does it compare to the state it was in? Okay, so this is exactly the meaning of the product. How does it compare to that? So if I was a spin, a line onto B0, nothing happens to me. And then I compare to myself, this is 1. I didn't change my orientation, right? So now I'm just calculating this part, magnetic part, because all those other parts are just numbers. When you do that, then you end up with just a number. And now the energy becomes a number multiplied by another number. And if you repeat, and I will go quickly through the same thing, for the different spin orientation, then you will get exactly the same thing. And at the end, you will see here a number multiplied by a number. When you look at the Hamiltonian, you know already the energy state by a factor that is not yet known. But still, you may just, by looking at the Hamiltonian, you can know what's going on. So now when you write the difference, then you see that here in this case, the difference between these two numbers makes 1, and then you're left with a number that was just a part in the Hamiltonian. So why do I need that? Because now I need to describe surfaces of energy. A surface of energy where this result doesn't depend on the orientation is a sphere. But a surface of energy where it depends on the orientation can be described by harmonic spherical harmonics approximately. Actually, in our language, we don't call them spherical harmonics because there is an approximation in the Schrödinger equation. We call them tensor of rank 0, of rank 2, of rank 4. What is the difference between a spherical harmonic and a tensor? Actually, if you remember a little about Schrödinger equation, there is a complex potential in that bloody equation that you want to remove. And the best way to do it is just to say, well, this has a spherical shape. And then it simplifies things, and it makes the solution a little bit specific because they are symmetrical, not only by a center, but by an axis, the axis of the interaction you are dealing with. When these are electrons, you are not dealing with a magnetic moment, you are dealing with an electric moment. Okay, so if I come back to my tensors, they are very close to spherical harmonics, and then I can now describe any interactions with those shapes. After a little while, you know all those shapes by heart. So, there is a little bit of noise in the back.
Ese es el, todavía escucho voces de los de allá.
Okay, maybe you don't hear. I do. If I take an interaction that has an axis of symmetry, so eta, the eta parameter that has been introduced to you before, is equal to 0, then you can describe a tensor of rank 2 by an orbital of 0,0 symmetry of D-type. So this is what you will get, and if for any reason you are having a distribution of orientation of that energy, for each orientation you will get a frequency difference, an energy difference that will correspond to one sharp line. Now, if you're having a distribution, then you will get a histogram of lines, and this leads to a very large broad line. However, the shape of that line will tell us about the shape of the surface we are considering. So there is a direct relation in your head between the shape that you can recognize on the spectrum and the shape of the object you're measuring, and those objects are just surfaces of energy at the macroscopic level. Did you ever think that in chemistry we don't see things? We see them only in our head. You can't put your finger on an electron. You can't put your finger on a nucleus. But here, with the shape of that type, you can immediately look at the shape that is inside your sample. Now, if you're taking a single crystal, then if you align the single crystal, for each orientation, you will get one line. And now if you patiently turn the single crystal, what you will get has rotation patterns. Now, obviously, if you're taking those orientation, make a histogram, then you will recognize the shape of the surface. But here, what you can do out of that is just building in space with the coordinates of your crystal the surface of energy of your interaction. So this is something that at the beginning of NMR was believed to be able to solve structure like we do in X-ray diffraction. So these are the different shapes. If you are having an axial symmetry, you will have two orientations that are coincident, the histogram and the limit, because the orientation of your surface can vary only from 0 to 90 degrees from 0. So you're having discontinuities, and this is an axial symmetry. If you're having an arbitrary distribution for the surface, then you will have 3 discontinuities, and actually if you're able to spin at a magic angle, as we will see a little later, then the average value of that is the isotropic chemical shift, which is what you measure in liquid state. This is an experiment that has enlightened in the 60s the whole chemistry community. Why? Because if you look at the span of the anisotropy, when you're dealing with objects that are containing carboxylic acid and aliphatic acid, then you know for sure that the one with the smaller span is an sp2 carbon, and the one with a larger span is an sp3 carbon. So that was the first, I would say, NMR imaging of the shape of surfaces. And this has led to the ranking, to the tables of isotropic chemical shift in liquid state. Why? Because now you know that you're having a range where you're having the sp2 carbons and ranges of chemical shift where you're having aliphatic carbons. Now, another aspect is the tensorial character of interactions. This is not quantum mechanics, actually. It is something that is related to elasticity. If you want to laugh a little, what is actually the orientation of the surface of your mattress before you lie down on the mattress and after you lie down on the mattress? It has been distorted. So the normal vector to the surface is given by what is the normal surface at the beginning, what is the normal surface at the end. And in order to relate one to the other, you need just a matrix. This matrix is a representation of the tensor of elasticity, how you deform your surface of energy. However, if you want to be clever, you would say, well, the constraint I know, this is my magnetic field. The orientation of the surface I would like to know, okay? So if you know what is the orientation of this new normal to the surface, then the deduction from the original normal to the final one is just given by a rotation in space. So your magnetic field has distorted something, and the net result is that the effective field at the nucleus is not the external field. It has been distorted by electrons that were around, exactly like a mattress is made of foam. And then you end up with something that you have already been described with. We are not dealing with the three numbers that are there. These three numbers that are the screening numbers, you combine them in order to have the isotropic value, the anisotropic value, and the asymmetry parameter. As I told you, the isotropic value you will recognize on the liquid state spectrum. The anisotropy is the span that you can read directly on the spectrum, and the asymmetry parameter is deduced from the shape of your spectrum. Now, actually, the nightmare is that we are dealing with many interactions. And those many interactions are something difficult to deal with, because are you going to acquire everything, every information about your sample, and then try to represent your sample? This is not at all the way it works. Solid state NMR is a little bit like sociology. Actually, you are having carbon atoms. This is a family. You are having hydrogen atom. This is a village. Okay, and then you may have also another village like fluorine. And all those guys are just interacting. From time to time, they're collaborating. From time to time, they are not at all. And then the question is, what do you want to know about the society? If you say everything, then you may leave that room immediately, because we can't do that. Okay, this is absolutely something that we can't do. But if you say, I would like to know something, then the question now is the following. Aha, if you want to know something, you have to leave the information inside your spectrum. But the things that you're not interested by, you want to ignore. Ignoring means canceling. Canceling means I would like that the average Hamiltonian is 0. That's a translation between canceling and Hamiltonian. Let's go back to the expression of the Hamiltonians. When I said that this is a subset, a very small subset, let's think about a chloroform molecule. It seems to be simple. Chlorine, carbon, hydrogen. Now, make a list of that. You have chemical shift for carbon, for chlorine, for hydrogen. Then you are having coupling constant between hydrogen and carbon, hydrogen and chlorine, chlorine and carbon. And we may keep on doing with the dipolar interaction. For the chlorine, it will be also a quadrupolar interaction. So actually, when you end up with the full Hamiltonian, you write 2 or 3 pages of terms. So how can you make something decent out of that? This is really impossible. So the best way to do is there any generic way to look at the Hamiltonian in such a way that if I say I'm interested by that, then I can cancel all that. Okay, so that's the spirit of it. This has been engineered years after years, and now this has reached a simplicity that is absolutely amazing. This is a general engineering technique for simplifying any sort of Hamiltonian to the value you want to have. Hamiltonian will be always represented by a sum of terms, the scaling term, the space term, and the magnetic part, for all of them. So you may have a large sum. Every term in the sum can be decomposed the same way onto a unique basis of surfaces. Okay, so if I just consider the dipolar interaction, magnetic part, this is heteronuclear, this is the scaling number, and this is Legendre polynomial. So you can even reduce that and look at one term, this term here, and you look at the three parts, scaling, space term, magnetic term. So now we can describe almost the whole variety of experiment that we are going to describe during the talks with just one single page of small notations, and then you can follow all the complexity of the actual development of NMR. What is the purpose of that? What do you want to do? First thing, you want to suppress interactions. You don't want to keep interaction, you want to suppress interaction first. Too complex. So, you have to average the Hamiltonian. Let's consider this Hamiltonian, and I would like to have an average value. What can I do? Average means this is changing with time. If it's not changing with time, then the average is just the Hamiltonian you started with. So what would you like to do in order to suppress Hamiltonian? You have to make those interactions dependent on the time. How do you do that? Well, you can spin your sample, or you can move your magnetic moment. So when here I put in blue one part of the interaction, what I do is say, this is now going to move, is going to change with time. So if now I move to the magic angle, what is the magic angle? It's the angle for which the axis of the second order polynomial Legendre has an average value of 0. So this has been described by my colleague, and I've told you that already. So there is a possibility. You spin the sample, the Hamiltonian is changing with the orientation, you measure over a long time enough, and then this part of the Hamiltonian has disappeared. First technology, moving the sample. Second technology, decoupling. Decoupling means what? Now you're going to act on the magnetic moment. You want them to change their orientation. So you will apply a radio frequency field to your coil. This will generate a magnetic field oscillating, and this will change the orientation of the magnetic moment I am considering. So it could be fluorine, could be proton, it could be carbon, it could be anything. But now, look, if I'm moving only one of them, the average value of that magnetic moment can become 0. If it becomes 0, then the whole Hamiltonian disappears. Now, you can also apply on the other spin. And then this is another way to decouple. Here you will decouple in proton, but you will observe in carbon. But you may want to do the inverse, and then decouple in carbon and observe in proton, or many other schemes, okay? So this is the way to do decoupling. Now, hey, you don't want to lose all the information. You're observing a sample, you want to extract some information. So if you kill all the information, this is not a very bad position, a very good position. This is a very bad situation. So what do? You want to recouple. You want to reintroduce the interaction you are interested by and not all the rest. So suppress everything and then reintroduce what you're interested by. How do we do that? How? This is a key aspect of high-resolution solid-state NMR. This is definitely a key aspect. Why? This is a general theorem that in principle you have learned years ago at the beginning of your high school, of your university studies. If you take here a time dependence for the orientation of your interaction or for the orientation of your magnetic moment, the product of the average is not the average of the product. I repeat it because this is very important. Let's give me a picture for it. Probably when you were children, you like to use tops or places where you spin with other colleagues or friends. But there's a possibility. You jumped onto it, it turns, right? It spins. But your friend stays there, right? For him, your average position will be just along the axis. He looks at the game, and so he will see that. But now, let's think that the friend is running around, moving at the same time. He's looking at his friend as being just always at the same position, relatively to him. So both situations are very different. If you're in asynchronous mode, then those two averages can be the product of each other. If you are in synchronous mode, this is no longer the case. So if you want to make something that is non-zero, what you have to do is change the orientation of magnetic fields, of magnetic moments, synchronously. However, there's a third term over here. So here you have to think about the rotation at the magic angle. This is also generating something. Now let's assume that we have taken care of that. You have also to take care of this spatial part. Is it changing with time? Or is it just a constant aspect? If it's a constant, then it's a number. You can just put that in factor, and then you have just the product. Now, if you synchronize the motion of your rotor and the motion of your magnetic moment, then you can do a lot of things. This is exactly the basis of high-resolution solid-state NMR. You need to average, you need to reintroduce. Reintroducing is exactly what you want to do in order to get one information out of your sample. Now, is that the last item? Not really. You may have, in the sum of your Hamiltonian, oscillating terms, cosine, sine terms. And actually, you are having a sum of them. And again, this is much too complicated. You don't want to keep all those. So what do? You repeat the same experiment 1, 2, 3, 4 times. And then when you put your receiver, when you orient the coil detection towards your sample, then you may change the phase of your coil detection. The coil is not moving. I have just to warn you. You're already moving the sample. This is a lot. But you're not moving the coil. You're just changing the phase at which you do the detection. Okay? And this is repeating the same experiment with different phases. And then you sum up all those experiments, and you keep the oscillating term that you were interested by. This is called coherence selection by phase cycling. You see what happened here? The Hamiltonian is not average in a single situation. It's average over several experiments. acquired 1, 2, 3, 4, in some cases 120, okay, and even more. And then you sum them up and you extract the part you are interested in. So with those 4 tools, this is enough. You can design almost any type of experiment that you would like to get in order to analyze the sociology of your sample. Who is close to who? How this cluster is organized compared to another cluster. How those molecules are far apart or very close. How the structure of a crystal is organized. But the situation you are having there, at contrast to X-ray diffraction, you do a single measurement and then you pay a lot of time doing the software analysis of a single measurement, and then you can get the structure. In NMR, this doesn't work this way. We work the pieces of information one by one. What is the advantage? You can pinpoint on what you are definitely interested. What is the inconvenient? Well, you can't get everything at the same time. So you cannot get both aspects at the same time. So usually NMR is a not so sensitive experiment. Experiment in NMR can be 2D or 3D experiment, they can be quite long. So what is the objective now of working on solid-state NMR spectroscopy? To find ways where you can optimize the sensitivity and the resolution in such a way that you can access with your finger the information onto the spectrum. When you look at the liquid state spectrum, what do? You look at lines, and you know that to each line there is one chemical function. This is exactly that type of simplicity that we want to get in high resolution NMR. So now I'd like to go a little bit in more aspect that will just address the different talks of this meeting. I'm not going to go through magic angle spinning because this has been described. But one aspect of magic angle spinning is suppression, reintroduction. If you look at the spectrum, that was a static spectrum. Here I modeled a phosphorus spectrum, and I had a single site. You start spinning. You see that you're modulating the histogram of your frequencies that are now becoming a comb of lines. Separated by what? Separated by the spinning speed. If you spin a little faster, this will go away. If you spin a little faster, then the intensity of the spinning sideband is decreasing. If you spin infinitely faster, this we don't know how to do, but you will get the isotropic chemical shift. You have erased, cancelled the anisotropic part. But you see that, okay, fine, you've been working at high speed, but now you're interested in the anisotropic part. Slow down the rotor. Then you will collect the intensities there, and out of a little software close by the spectrometer, then you will recalculate the anisotropic part. So you have, this time, both aspects, isotropic and anisotropic, and the resolution. Why? Because you have separated lines. In between the lines, there is some room for measuring different sites. So shaping the Hamiltonian is definitely something that is of utmost importance. You can recouple homo and heteronuclear dipolar interaction. You can decouple homo and heterodipolar interaction. You can reintroduce space as isotropic to anisotropic correlation. And you can also transfer polarization that will allow you to gain in sensitivity. Cross-polarization. I have to say a few words about that. Why so? Because most of the experiments that have been recently developed in high-resolution NMR are experiments that can be described by exactly the same formalism. In the case of CP mass, this is the oldest experiment for high resolution of solids. This is one of the widest used. Well, there are two used experiments, single pulse and CP mass, right? Anyhow, in solid state, CP mass is probably about 70 to 75% of the experiment. Now the question is, do we understand how it works? The answer is not really. We understand much more than at the beginning, but we do not understand very much how it works. Can we bring back CP mass to exactly the same formalism that we have used? Because this is so simple, it's general. You apply things, you decouple, you reintroduce the interaction, you play with that. My credo is the following. Yes, we can do that. And there are still some subtleties, and there are reasons why CP mass is so popular. It is so popular because it's a complex experiment that cancels more or less all the defects of one aspect by another. So I will just pinpoint on the fact that you have to know that CP mass can be as well understood as an inept experiment. It could be as easily understood as other type of experiments. However, how do we do the representation? First of all, we are having two systems. In the static case, let's consider a CH pair, not a too complex system, okay? Then you are having protons, you are having carbon, and what you want to do is just a way to transfer the sensitivity of proton to carbon. How are you going to do that? Actually, if you want to do that, then you have to find, like in any physical system, if you want to exchange energy, you need to have a range of frequencies that are common. Without any frequency common, you cannot exchange energy. You are in an adiabatic system. So if now you apply radio frequency on the proton and a radio frequency on the carbon that are making now the difference in level of energy, then now there is a common frequency that you have introduced into the sample. You put the atom, their energy, into contact. That's what is said in textbook. Now, this is a static case. Now, if I'm spinning, I have something that is a little bit complicated because I'm manipulating the magnetic moment of hydrogen and carbon, but I'm also spinning the sample, so I'm modulating the space part by that. So actually the general formula is that you're having for every difference between the radio frequency of proton and carbon, if this is a multiple of the spinning speed, then you're having an exchange in energy. If you don't, then there is no exchange in energy. Let's now sum up. How is the CP mass experiment working? First of all, you put your sample in the magnet and you do nothing. So the magnetic moments are just orienting along the B0 axis. And now what do? You pulse on the proton, and the proton magnetization is along XY plane, perpendicular to Z. And now, during a long contact time, you apply radio frequency fields that are making the movement of magnetic moment of equal frequencies. If you're spinning at the magic angle, you choose one of the conditions, that is this difference between proton and carbon is a multiple of the spinning speed. And during that time, then you're changing the population of carbon. And as the proton is abundant, when you have changed almost the whole population of carbon, you've only consumed 1% of the magnetization of proton. This is a good reservoir. So here you change the population of carbon, and now you're going to measure carbon, and what do? You decouple. And so you observe only the isotropic part of carbon because you have been spinning at a magic angle and decoupling the protons. Let's put that into average Hamiltonian. So when you're moving at a magic angle, this part is moving. Now, when you're just doing the contact, you're moving at a magic angle, and then you're having the motion of your two magnetic moment. So now, during that time, the Hamiltonian is not zero. You have reintroduced the dipolar interaction. And now when you're measuring here the carbon, actually what you do is that you're observing something by just making one of the radio frequency moving, and then you're averaging again that Hamiltonian, you're left with only the isotropic part of carbon. So why did I go in details about those examples? Because every experiment can always be decomposed this way. You look at the interaction you want to consider, you pick up on the series of information you are interested, the parts by which you are interested, and now you look in the library of pulse sequences, how to cancel this one, how to reintroduce this one, how to get the correlations if it's a 2D experiment between one information and another information. And now you are really playing on the playground of solid-state NMR. I will keep on one aspect that is a subtlety, but this will put some light on more difficult experiment. I don't want to explain into details, but when you're doing CP mass, you have the carbon and the proton part, and you're also having dipolar homonuclear part, dipolar heteronuclear part. And actually, what I've described just a little before is just a slight oversimplification of the CP case. But to get started, this is enough, okay? But when you keep on working and optimizing CP mass, then you have to consider some things. What do you do when you change? You apply during the contact time, you apply a radio frequency on carbon, but you would like to know experimentally what would be the optimal radio frequency field for proton. So what do? You take a fixed radio frequency in carbon, and then you repeat the experiment several times with different radio frequency field on proton. Every time you find something that is red, it means that you're having an intensity that is high. Every time you're having something blue, it's very low. So if you take a slice here, this is what you will get, oscillation. And these are called Hartmann and match conditions. Every time you're having the rotation period, then you're having a maximum here. Now, the question is, okay, fine, so I understand. If I want to optimize a CP mass experiment, I have to choose a radio frequency field for carbon and optimize the radio frequency field for proton. Clear, you got the message clear, that's fine. Then you take a trace here, and then you're going to choose something. Let's say, to choose the condition here. Here, you will get a good intensity for carbon. Now, if you look here along that line, this is the intensity that you will get. It varies with the strength of the radio frequency field. If you're working at too weak frequency field, the transfer is not very efficient. But if you increase, and then instead of working here, you work over there, then you will be very high. The choice of the value of the pair for the carbon and proton is a critical issue. If you want to have full sensitivity, you have to understand that. Actually, this curve remains for people that are used to relaxation. This is the relaxation in the rotating frame that governs that intensity. And so if you are changing the radio frequency field, you are changing at the same time the relaxation time T1 rho. This is another issue that I will not discuss in too many details, but I will pinpoint from time to time. In solid-state NMR, you are definitely manipulating T1s, T2s, and T1 rho. T1 not really, but T2 and T1 row absolutely. And this is an advantage that you don't know in liquid state because the job is done by the solvent. Your molecule is just bumped by the solvent. The last item on CP, and for those that want to be started, having hands on the instrument is a critical issue too. Actually, I told you at the beginning that the coil is not having a homogeneous radio frequency field. Usually, if you take here a coil that is a bad coil, okay? This is the distribution of radio frequency field for the carbon. And this will be for the proton. You see, they are off-centered, and they are not having the same span. So take a slice here, and plot here the coordinate, the radio frequency field of the proton and the carbon. And now follow the slices. You will see that actually your slices are lying at different positions concerning the ratio between radio frequency field of carbon and of proton. They are not fulfilling the Hartmann condition everywhere. Some are not. Now, if you improve a little bit the homogeneity of the coil, then obviously you have much narrower curves. Is it an advantage? You would say, that's nice. If I have a perfect coil for proton and carbon, that would be nice. No. Why? Because some sites are just having their position just on the Hartmann match. And some others that are differing from the radio frequency plus the offset of their site will be ending in just a well here. No intensity. So we are very lucky that actually what you can do is just you change progressively the radio frequency field of the proton, keeping fixed the one of the carbon. And then this is what I have plotted here. Every time you're having a value, every time you're having slices that are positively responding. And then if you romp this, then the whole sample, or almost the whole sample, is cross-polarized. So I just wanted to pinpoint those aspects because as CP mass is one of the most used case, what is not really well understood is the optimization of CP mass. It's not exactly in the center of recoupling and decoupling, it's slightly off-center, but we will have two talks on the different aspects to talk about that. Be careful. If you buy a probe that goes much higher in spinning speed, then there is one Hartmann match that disappears, is the central one. Why? Because actually the spinning of that makes this cancelling the heteronuclear recoupling, and you are left with zero quantum condition here and double quantum condition there. I'm not going to detail here yet zero quantum, single quantum, double quantum, but this will come a little later. Finally, you will see in the talk about dipolar recoupling that while you do increase the contact time for your CP mass experiment, then what you observe are just oscillating parts. And those oscillating parts are due to what you have reintroduced, which is the dipolar interaction. So out of that dipolar interaction, what you can do is measure distances. In the talk about decoupling, there are many situations where cancelling the coupling is different. So actually what you need to do is just understand why you have different schemes and maybe the choice for the family of experiment you're dealing with that you're likely to make. And the last item that is not the simplest, but this is just in a full line of what I've explained you just before. If you can decompose Hamiltonians in sum of 3 terms, and now you can now decompose them into symmetries in such a way that you know immediately if you want to suppress terms, when you apply a suppression to that term, to which term it will apply at the same time. So you're going to suppress this one and all the others that are having exactly the same symmetry. So this is something that has been developed by Malcolm Levitt's group, decomposing Hamiltonian into their symmetry. The space part, the spin part, they are having different ranks, and they can be decomposed in a very finite number of symmetry. So now when you want to develop new pulse sequences, you will consider that you want to select part here, so you want to keep some part, you want to average some part. And this has been done, and now this is used generally as one of the aspects of the latest development in solid-state NMR. You can design pulse sequences at will, depending on what you want to keep and what you want to suppress. Few applications are going to appear also in the different talks. Detection of polymorphism in pharmaceutical materials. This is today a technique that is emerging as one of the new techniques for regulatory issues for the Food and Drug Administration or for its equivalent in Europe. You can now also develop 2D experiment where you are measuring something that you correlate to another time that you make incremented, and then you can get 2D experiment that are correlating the proton to the carbon. But if you have done a little bit of liquid state NMR, you know that very well. In some other talks, you will hear about quadrupolar nuclei. Those quadrupolar nuclei are multi-level systems. And actually, for a long time, they were thought not to be brought to high resolution, but they have been with 2D experiment like MQMS and STMS that will be presented later. Motion can be explored. If you're having motion in your molecular compounds, you can run motion that are just dealing with the anisotropy modulation by motion, and this will lead you to the parameter of motion without modeling. And finally, you can also study exchange in solid state. And for example, if you're exchanging proton and oxygen here, all the carbons there are just inverted, and you see all the pairs that are inverted. That shows exchange cases, so you can follow the dynamics. And now I would like to finish this talk by expecting that actually have shown some aspects of the basic of high-resolution NMR that will allow you to enjoy the playground of high-resolution NMR, depending on what materials you're dealing with.
We have some time for one question.
You may know a little bit more, because my second talk will be a little shorter.
Ok. Él va a dar otra presentación, entonces podríamos seguirle. Hay un coffee break y si tienen alguna pregunta pues pueden abordarlo mientras en el coffee break. Seguramente va a abordar algunas cosas más sobre este tema en su segunda charla. Le agradecemos al doctor Tolel su participación. Thanks a lot.
Es sobre desacoplamiento heteronuclear. Como el doctor Cepeda nos ha mencionado, el doctor viene de la Universidad de Versalles de San Quintín. Entonces vamos a continuar con él en esta ponencia.
Muchas gracias. Actually, now that you've at least reviewed some concept and principles, and also an approach that defines a methodology for high-resolution solid-state NMR that is very general, that is extremely flexible. This flexibility exists because there are many things to do in different type of situation. I would like to ask if you wouldn't bother if I can take my jacket off, because it's really hot over here. So for women, I will not strip off very much further. So actually, recoupling has inspired me and also some of my colleagues that if you are able to recouple, then you're able to measure distances. And as my colleague has expressed this morning, this is really the case where polygamia is really useful because you're also measuring distances with X-ray diffraction, with electron diffraction. You can model compounds, and then you can push the resolution of crystal structure to limits that are unknown if you are using only one technique. So for those that are interested, at the end of the month of May, there's a meeting that will mix people from all those different fields: NMR, electron microscopy and diffraction, XRD, modeling. This is held in Porto. It's quite convenient to go to Porto. And it's in Aveiro, but the airport is in Porto. So this is just the end of the advertisement. Back to the movie. If I compare the different terms of the different Hamiltonians that are describing the recoupling, then you can recouple by decoupling or by J-coupling. And you can immediately see that there is one clear difference between those two Hamiltonian parts. One is orientational dependent, and the other one is not. So there will be small frequencies with J-coupling that you know from liquid state NMR. You are having multiplets, and those multiplets are as narrow as without decoupling. So this comes from the spatial part here. So recoupling can imply different interactions. Why should we reintroduce dipolar interaction? First of all, as you've learned this morning, I mean, these are just distant containing information parameter. You are having the cube of R, the distance between nuclei. But now you're having problems because you're spinning at the magic angle, and so those dipolar interactions are removed. So what you should do is just rotor synchronize, as I have explained a little bit before. Now, there are two types of distances, homo and heteronuclear, so the same or different nuclei. So we will concentrate in this talk about hetero cases. There are different ways to proceed. You have to choose in a pulse sequence what you're going to measure. Measure meaning what you record during the FID. You're measuring one given site, and this given site will be modulated by the information you want to measure. Again, I repeat because this is quite important. If you want to select and to edit interactions, the spirit of high resolution is to use one interaction that you're measuring, single quantum, during the FID, and before that, you may generate something that is modulating this signal. So you are doing, most of the time, an indirect measurement. Okay, for example, you want to know if your neighbor has eaten, okay? You look at your neighbor, but you've put the balance, so he goes to the house, wait, then goes back, wait, and you know the difference. You have modulated the amplitude of the balance. This is an indirect measurement, and then you can say, wow, the dinner was great. I mean, the weight difference is really huge. Okay, so this is an indirect measurement. So what we can do now is use J or D. I've told you just before that in cross-polarization we are using D for the way to do the cross-polarization. And then we can generate experiments that are just the equivalent of an inept experiment, but instead of using the J inept experiment, then you can use the D inept experiment. Now, with two transfers, then you do an indirect detection. This is doubly indirect in this case. And you can generate, for those of you that are familiar with high-resolution liquid state acronyms, DHMQC. This is one of the plague of NMR, is that you need a full dictionary in order to recognize the names. Okay, so HMQC, HMBC, and NOSY, and ROSY, and whatsoever, and then you turn the pages, and you turn the pages, and there are so many acronyms. So don't be afraid by those acronyms. For one simple reason, if you're started in NMR, you find dictionaries of pulse sequences. So actually, you don't have to remember, like in China or in Japan, the 35,000 characters that are just describing what you want to do, okay? It's much simpler than that. But you have to be careful and not to be fooled. After a little while, you will learn the most important pieces, and then you can memorize most of what you need. So I've already shown this scheme for CP transfer, and when you do that, you see that compared to the direct CP, there is an interval in time between the 90-degree pulse and the log in such a way that here the proton that has been brought into the XY plane now changes its phase by just the action of the isotropic chemical shift. You couldn't suppress that, okay? So the isotropic chemical shift is modulating the phase of the signal. So actually, if you were measuring here an FID, you would get a normal proton spectrum. Now, you're just incrementing one by one, and for each increment, you measure the carbon. And here you do the CP case, transfer to carbon, decoupling, observe. When you do such an experiment, the carbon spectrum has been modulated in amplitude. Why? Because actually when you transfer here, you transfer with the part of the magnetization that is along one axis, the one to which you cross-polarize. So here, with the evolution of T1 by increment, then the part of the proton magnetization that will transfer to the carbon is modulated, and this modulation is reflected in the carbon. So actually, what you do is measuring indirectly the proton spectrum, which is here, by looking at the spectrum in carbon, repeating the experiment many times for different T1s, and do the Fourier transform. So the modulation that the carbon has been submitted to, is reflected into doing the Fourier transform of those modulation of one carbon column. So this is the principle of the 2D. It applies to almost all type of 2Ds. You can modulate in amplitude or you can modulate in phase. It is obvious for this case, which is ibuprofen sample. I've chosen that case because ibuprofen is what you need when at the end of my third talk you will go to dinner, to the meal, because you need to have ibuprofen to clarify a little bit your ideas. So now you can do that with many other cases. If you are considering a material that is called VPI5, this is an aluminophosphate, and it's a nanoporous aluminophosphate. What you want to know is how many inequivalent phosphorus in the structure you have. And here I have to remind you that even if chemists believe normally that everything can be described by molecule, this is not true for inorganic crystals. In an organic crystal, you are having networks, you are having lattices, you are having an infinite number of covalent bonding. You don't have a molecule. A crystal that is completely covalently bonded is not a crystal, is not a molecule. Anyhow, what you can measure, if you are detecting phosphorus, is the number of inequivalent atoms that you are having in your unit cell. And I've shown, just my second slide, I've shown René Just AUI. René Just AUI was thinking that the unit cell was the meaning of molecule. Okay, an error that was corrected by his first student. So now you are having phosphorus. But if you want to analyze, now this is your strategy, you want to analyze how this network is organized. Which atom is close to which one? You need to have a technique to know who is my neighbor. And so the question here is just to use a net core experiment that will just use neighbor, meaning living close by, but not having a common corridor. That would be a covalent bonding, right? Here is just neighboring. So you're having dipolar interaction. And then if you are having as indirect detection the aluminum, every time you are having here an intense cross peak, it means that you are having definitely here a neighboring situation. Now, there are cases for aluminum, chemical shift, as you will learn a little bit later. Chemical shift is not the only component in the Hamiltonian that survives when you do magic angle spinning. And so actually the line width here contains more than the isotopic chemical shift, but contains also the quadrupolar interaction. So if you filter now this experiment on aluminum in such a way that you remove the quadrupolar part, then you're left with an isotropic part, and then you can see that you're winning in a resolution. The gain is obvious. So instead of saying that you're having 3 phosphors and 3 aluminum, you can immediately see that you're having different type of aluminum. However, if you want to do CP for quadrupolar nuclei, as the quadrupolar nuclei are having a multi-level system, then you have to change the scheme for the efficiency of the transfer from the quadrupolar nucleus to the spin 1/2 that you're measuring here, phosphorus. So that's a method that has been developed by Jean-Paul Lamoureux. And actually, it is a quite important method because the cross-polarization of quadrupolar nuclei to spin 1/2 has having many zeros. So if you tune slightly your CP experiment as usual, you're very likely to end up on a 0 transfer. So if you want to avoid that, then there is a scheme that is different, quite simple scheme, and then you can get experiment with this way of doing the transfer and having the correlation between phosphorus and aluminum. Now, you can revert things, and this is something that people are not aware of, is that you can also detect things in one direction or in the other direction. Why do you choose to detect usually carbon and do proton in the indirect dimension? Because the resolution for proton is not that great, and the resolution for carbon is really higher. So you pay the price for the resolution in detecting carbon and leaving proton doing the evolution. Now, if you are here, you can also consider that you may detect aluminum and leave the dipolar interaction between aluminum and phosphorus evolve during the phosphorus, on the phosphorus side. So this is your choice. And actually, if you look at the different sites, here you are having the second order quadrupolar broadening, and my God, the resolution of the phosphorus is not formidable. Now you apply the same empty CP mass technique and on phosphorus to sodium case, and you can see that now you are having very well resolved results. So this is something that was done with CP mass scheme. Now if you're considering HMQC, it's one of the simplest sequence that allows you to do the indirect detection X to Y to X again. So look at the complexity of the pulse sequence. Aluminum excited, okay, and then left for evolution. And after a little while, then you are having here 180 pulse on the phosphorus side, a refocusing pulse here on the aluminum side, a second 100, and then you detect on the aluminum side. So this is the scheme for JHMQC. You don't need to do any recoupling in the case of the J coupling. Why? Because you can spin at the magic angle, but you're not removing that. It's not orientation dependent. It's still there. It survives. Now, if you want to do, and you can get good correlations, JHMQC, between aluminum and phosphorus, always on nanoporous aluminum phosphate cases. What happens if you want to transfer that pulse sequence and you say, J coupling, yes, okay, good. But I would really like to have that as a decoupling. Well, now there is a slight difference. Why? Because the scheme is just the same, 90, pi over 2, 180 over there, and then you measure here, you decouple here. But you're spinning at magic angle. If you spin at magic angle, you are not having any decoupling left. So what should you do? During the evolution here, you have to reintroduce the dipolar interaction. Okay, and during the echo here, you have to reintroduce the interaction. Look at the parameters that are critical here. This evolution period is an integer number of the number of rotation of the MAS. This has been synchronized. And because this has been synchronized, then the product of the different part of the Hamiltonian is no longer the average Hamiltonian, is different now from the product of the separated evolution of the Hamiltonian. This is what you do here. This is just that. So you keep the sequence and you add a recoupling sequence here. Obviously, as I've explained just before, you can do this in one direction. You can do that in the other direction. So you can do the recoupling here. Why? Because actually, when you're considering that product, that is the space part, I1 and I2, you can apply the dependency of the magnetic moment orientation on the first nucleus or on the second nucleus. So you have the choice. And this will depend on the equipment you have. Maybe you don't have the channel that allows to do all the experiments, so you will choose the one that is limited by your equipment. So there are cases of that type. However, there is a general recommendation that will appear a little later. When you're doing that on this experiment, you're having here a quadrupolar case. And so you can detect the quadrupolar case or you can detect the spin 1/2 case. The recommendation is always to do the recoupling on the spin 1/2 sides. Now, these are experiments that are meant for biologists. Why? Because actually, when you're studying DNA, peptides, proteins, and things of that sort, then you're dealing with amino acids. And when you're having amino acids, then you're having sequences of proton, carbon, nitrogen. In the recent development of those pulse sequences, the DHMQC can be used between proton, nitrogen, and then, as you can see, you're just doing the same thing, recoupling here on the proton side, having the HMQC scheme for all the rest, recoupling here, and then you can detect nitrogen 14. For those of you that have already a little bit of experience of liquid state NMR, nitrogen 14 is not the easiest one. It is very abundant, no problem, very low gamma, very large quadrupolar interaction. So this is probably not the material that is the best suited for detection. However, with the reverse detection, then you can definitely improve the detection schemes, and today we're just probably going to a routine type of measurements with a little bit still development on the vendor and spectrometer maker side, and a little bit development also on schemes that will excite a little bit more and a little bit more sensitivity on the nitrogen transfer. Okay, now I'm just playing a game that is actually what I meant before, is that to teach you how to recognize a pattern in a pulse sequence. Otherwise, I can show you, as I've told you, 450 pulse sequences, and all of a sudden you wouldn't be able to read anything. Most of you probably have learned to sing without reading music. So you know that you can do something, but you can also read music. Here, in the case of NMR, for complex sequences, it's much better to know how to read pulse sequences. So in this case, if you want to do a DHMQC, and like I've shown in a previous slide, you want to improve on the quadrupolar side. Okay, you will see, I've just anticipated a little, you will see on the quadrupolar courses that there are different techniques, MQMAS, STMAS, slow CTMAS, QPAS MAS, and things of that sort. So they're different type of solution depending on the cases of the quadrupolar nuclei. However, once you have transferred from proton to sodium, you may have the pulse sequence that is just the HMQC part, and then you can add into this scheme a filtering scheme. So between the evolution of those two pulses, what you will do is remove parts of the Hamiltonian that were broadening your signal. You don't want to have that, so you may just start a first experiment, which is the simplest, look at the 2D spectrum, say, doesn't work the way I wanted it to work. And so you can add a filter here. So that's the way you can definitely improve on the resolution on the isotropic side. Here, the resolution was not so bad. Here, it's much better. So, now, there are spin pairs that you can analyze, and among the spin pairs, there are different techniques. As I told you, during CPMAS, there are many recouplings, actually. It's not only one recoupling. Every proton may transfer to one carbon. So if you look at the sphere around the carbon, you may have many protons, and all of them will, in a way, transfer. So the question is, if you are interested by measuring distances, how can you do that? How can you extract from all the phenomena that are taking place in the CP experiment, how can you extract the one that is leading you to the measurement of a dipolar interaction that is a single pair? The principle is the following. If you are considering an atom, a pair, and then you're just making a pulse that brings the magnetization to the XY plane. After that, you can do a train of pi pulses that would be synchronized onto the rotation period. So when you do that, and the magnetization here moves with the rotation, is inverted. Instead of doing an oscillation, sine oscillation, you're inverting it by the pi pulse, and then you invert again every time you apply that. However, if you replace the pi pulse here by a pi pulse on the I side, then the net effect is just the same, because it's a dipolar interaction, it's a pair, so you can act on one or act on the other. So if you do that, then you keep on inverting, and what you have done is just instead of having a sine part, the average value of that sine part would be 0. Here, what you do is just counteract for the inversion, and you have an Hamiltonian that is no longer 0. This is exactly what you wanted to do, but only that Hamiltonian that you have selected. Now, you suppress the pi pulse over here, and now for this sign, you keep on going, and now you're having the pi pulses. So this is exactly the spirit. Now you will have something that for that specific dipolar interaction will be here not 0, here 0. But there are many other pairs, but they have not been touched by this scheme. So actually, if you are now comparing this magnetization to the one that you are having here, here you have everything, and here you are having what the pair has refocused. So this is the spirit of the radar experiment. This has been calculated formally, and it depends on how you want to plot the magnetization measured on S compared to the experiment without the pi pulse here, or the difference between what you had before and what you had after for the second experiment divided by S0. If you plot those experiments, and then you Fourier transform them, what you get, oops, there's a slide missing, sorry. What you're having here, this expression contains actually the oscillation from the powder, and the oscillation contains the dipolar interaction. So, now, you can do that for pairs like carbon to nitrogen 15, and then you will get the same type of experiment here for the carbon, the nucleus that is detected, carbon, and the passive atom for which you would like to know the carbon to nitrogen distance. And as you are having a bath of proton, then you don't want those protons to interfere. So you decouple. You do a CP for increasing the sensitivity on carbon, and then you can here decouple there, and while you decouple there, you can also do a double quantum scheme here in order to keep the magnetization of proton active onto carbon. So these are the way to decompose the pulse sequences into bits and pieces. So when your eye goes onto a paper, I keep going and saying that you have to recognize the block. So if you want to get trained, the best thing to do at the beginning is just to take your pencil and to mark what are the different blocks. As soon as you have done that, then you roughly know how it works. So in the case of carbon to nitrogen, then you did get a radar experiment with a different contact, a different evolution period, and then you can see that actually you can select the pair that you want to measure, the spectrum at the beginning without a nitrogen pulse, with the nitrogen pulse, and this is the difference, and you see that you've measured the distance onto this CH carbon. So this is where the measure has been done. Obviously, you can try to do that also with REAPDOR, and the REAPDOR is just the case between a proton and a spin, a quadrupolar spin, and then you will start by CP. You will recognize the scheme more or less the same. Okay, simply here the S-spin is not excited at the center between the pi pulses here. So this, in a way, is also providing you with the same type of information. Those experiments that I've shown, radar and REAPDOR, were the experiments that were at the beginning of those measurements. And recently, and this is again an advertisement for Jean-Paul Amoureux Group, the advertisement is that there are many experimental limitations. So you have to be careful that your probe, your system, your sample is not fulfilling the requirement of the pulse sequences at the beginning. So you may just develop pulse sequences that are covering a broader range and that can be specific. You will recognize systems here that are, that are just exhibiting almost the same scheme, but with different efficiencies. Actually, this is something that you cannot really guess by yourself. You probably have to look at the calculations that you're doing into defining the efficiency of those pulse sequences. This is where the situation for just looking into the dictionary of pulse sequences and the requirement for each of them is very useful. You don't have to remember all those things, you just have to go into the list of them. The recoupling scheme on the previous samples have been pulse sequences that have been developed with the technology that I've shown before of Malcolm Levitt. So you can define what you want to keep, what you want to lose, and then if you do that and you just get the same type of radar curve, then actually those pulse sequences are just definitely improving. And more than improving, one of the advantages of those pulse sequences is that the curves there are universal curves. So you can use the same formula and get actually distances by just applying analytical curves. So this you can plug into a small computer and then analyze and fit the curve to the actual measurement and extract the data. So this has been applied to different type of molecule, different type of nuclei. In the case of tyrosine, the quadrupolar nuclei was oxygen-17, carbon and nitrogen and proton are the possible nucleus, and here it was just the proton, carbon, oxygen case that was analyzed. So, in a way, I've shown already several examples that shows that with the definition of old pulse sequences with new methods to analyze them, you can recognize what they were doing for recoupling, and now you can also develop pulse sequences based more or less on the same principle, but improving the efficiency tremendously. But then this is definitely the case where you have to do calculations. So I will end up by a list of references that you're having on the PDF file on the website. And for the recoupling case, I would like to stop here and listen or wait for questions. The questions can be on this talk or on the previous talk. Do not hesitate.
¿Alguien tiene alguna pregunta? ¿No? Bueno, ¿continuamos?
Yeah, so I can keep on going. You will save a little bit of time. If this is okay with you, I can do that.
Sí, vamos a continuar entonces. Él va a darnos la próxima plática y ahora nos va a hablar de el reacoplamiento heteronuclear. Entonces, pues vamos a darle algunos minutos para que continúe nuestra charla.
Thank you very much. Now I'm going to take off my tie. It's finished. It's my last talk. Don't have any hopes. Well, okay, for heteronuclear decoupling, that's something that is quite important. And the requirements for decoupling are several. Because actually, as you will see, the power that can be handled by a probe is not an infinite value. Actually, what you're doing, if you want to have an image in mind about the power that you sent into the coil, is like a laser. Actually, you're focusing, you're just restricting to a very limited part of the volume the energy that you are sending with your amplifier. So it's not only a requirement about the power of the amplifier, it's also the requirement of what you do to your sample. So reducing the power that is needed will appear as a consequence of the basic aspect of CP-MAS, and then once you have done here the contact and you do now the acquisition of the signal, you need to suppress as much as you can by decoupling. It could be simple decoupling, and we will see at the end of that talk that we can do also multiple decoupling. Anyhow, the principle is the following. If you do the acquisition with solution-like conditions, they are not synchronized, they are low power, and then you will get usually a signal here in carbon that looks like a baseline with noise. Okay, so in some old books, old textbooks, you can still find that actually the solid-state NMR was not possible. Though the discovery of the NMR has been done by both groups, by Felix Bloch and Pound and Purcell, on liquid state for Felix Bloch and solid state for Pound and Purcell. So be careful. Yes, the reason for it lies here. If you're using the conditions of one group on a solid state sample, it may be a complete failure. Now, if you do low power decoupling and the cross polarization, then you will get something that is slightly different from a baseline, but it's not gorgeous yet. Now, if you do CP, but high power decoupling, then you will get something that is definitely shaped, I would say. And now, if you do high power decoupling, then you will get, here's a resolution that is getting closer to the liquid state case. So what are the requirements then? If you try to do decoupling as you would do in a liquid, then what do you have to decouple for the liquid? No dipolar interaction, but the J-coupling. Why? Because your molecule is tumbling inside the liquid, and actually, due to the tumbling, then the average part of the Hamiltonian for the dipolar one is cancelled. Nothing left. So now you're left with J-couplings. And if you start here without any decoupling on carbon, then you will see the carbon that is coupled to all the protons that are around. But you can do now selective decoupling. You can just decouple one pair, one proton. Then you will suppress some couplings, but not all. Now, if you are looking at decoupling the whole range of protons that are coupled to carbon, then you will end up with something that is definitely decoupled for all those protons. One problem arises there and has been the subject of many studies for many years. Can you improve on the efficiency of decoupling even in liquid state when you are having protons that are quite apart from a chemical shift, but they are coupled to carbon? And actually, at the beginning of liquid state NMR, in order to be broad-banded, we had to use a large amount of power. And if you were not very careful, then your sample will be distilled, because you're heating so much the sample by using decoupling power. So this has been an adventure that has been shared by many. And one of my memories from a partnership between Malcolm Levitt and John Waugh. And for a long time, they have looked for different schemes that could do the same job of decoupling, but will reduce the power by at least a factor of 4 to 10. So these are have been many schemes like valse or many others. Now, again, you need a dictionary. Okay, now, what is the problem with dipolar interaction? The problem with dipolar interaction is that you're having a distribution of orientation. So for every dipolar, for one orientation, you will have a pair of lines. And now you are having distribution all over the orientations. And then you will have multiple pair of lines, and this will be the powder pattern average, all the orientation of the crystallites. And if you look here in units, the order of magnitude of this pattern is in the range of 100 to 200 kilohertz. So for that, you need definitely very high power. You need to be able to cover with something that is not selective, just one line, but all the lines together. So if you want to just do this and do in solid decoupling, then you will have to deal with this extent in the distribution of the powder pattern. Even if you are spinning at the magic angle, because when you're spinning at a magic angle, you will replace this static powder pattern by discrete lines, but you will still have to cover all those lines, and they are just covering about the same range. So, however, the mass may help, but in the case of protons, then you will see that you need to go to frequencies that are not the normal frequencies, that are not 5 or 10 kilohertz, but in order to improve definitely the decoupling, especially on proton, where the dipolar, homonuclear dipolar interactions are very strong, you need to spin very fast and still use high power. So the question is it possible to find a different strategy? So in the case, I would like to skip this one. This is something that tells you that when you're dealing now really with decoupling, you are not dealing with a simplified approximation that I've made in my previous talk. It's not only the monoatomic carbon and hydrogen and one heteronuclear case, but you have to deal with many other terms, and especially those nasty guys in dipolar, homonuclear, and less nasty are just the J coupling. So, but the dipolar here are definitely the part that you want to remove. So now several schemes have been designed, and instead of doing something that is a continuous application of the radio frequency, actually what you do is something that is modulating. Again, it's a time dependency, and you're modulating the phase of the pulses that are just stick together during the decoupling scheme. And this has been called, this technique, where you can optimize the duration of the pulse and you can optimize the phase of the second pulse, allows you to win tremendously on line width. So you're doing a much better job at using TPPM. So now the question is, fine, this is one way to go. You're having an idea that allows you to say, oh my God, if I create some other time dependency, I can improve on the pulse sequence. But then did I really improve on the power that was needed to do that? Actually, not so much for the case of TPPM. So people were doing now a rotor synchronized scheme like XIX. It's a scheme that is very comparable now that we have found something very comparable to TPPM, but instead of using a 0 phase and then a 5 phase to be optimized, then what you do is you use just an alternation, 0, 180, 0, 180. So you change just the sign of the phase. And then you optimize only one parameter, And when you do that, then you obtain a ratio between the rotation period, that is that block, and the tau p, that is that block. And this leads you to an optimization of the decoupling scheme that is less demanding, only one parameter. And so you can, again, try to see what you can achieve with this. This has given ideas to people, and you can also combine. What you do with this is you try, whatever you do in those schemes, you try to manipulate the magnetization in such a way that if you put some periodic aspect, in such a way that at the end, the Hamiltonian part of that is zero. There are two ways to do that in those decoupling scheme. You can play with the orientation of your magnetization, and you can play also with the phase. And by combining those two, then you distribute the magnetization onto a larger volume, onto a sphere, and by doing that, you improve definitely the decoupling scheme. Now, in a paper that was not too old, the question was, but if you spin very fast, are you still in the same regime? If you remember that the dipolar interaction is the product of three terms, the space term, the first nucleus and the second nucleus, then you will realize that it's not the same thing. If you're having a slow spinning speed, let's say up to 10 kilohertz, then the manipulation of magnetic momentum, of magnetic moments, is much faster than spinning the sample. So you are, in a way, in some sort of static, pseudo-static case. So you can consider the averaging of the Hamiltonian in a way. You're just manipulating the radio frequency field, and as the sample is now static, you're still facing the same problem, that you are having a very broad powder average. And this is the limitation. You're still keeping the very broad powder averaging. Now, if you spin much faster, maybe something may happen. And this is one of the bases of an experiment that has been published now 2 years and a half by Bodenhausen and colleagues. What happened if you apply decoupling, but you're changing the decoupling radio frequency strength as a function of the spinning speed that you have chosen, here 30 kilohertz. And you see that actually you are having interferences term between the rotation of your sample, the reduction of the dipolar interaction, and the spinning speed, and you are having different conditions that looks very much alike, conditions that we found in Hartmann and in rotation. So for n equal 30, 60, 90, 120 kilohertz, you had interferences between those two aspects. And so the question was just to try to find another schemes that could also work, but could work quite easily at higher spinning speed, that was inspired by the same type of reasoning that has been done before with TPPM and XIX. And again, here you find the alternation of the phase 0, 180, 0, the synchronization with the spinning speed, and then a parameter to optimize. So with this pulse, for which the acronym has been given to Pissarro, phase inverted supercycle sequence for attenuation of rotary resonance, then you have, like in XIX, the rotation and the period of the decoupling. And with this, these are the claims from the authors. If you apply CW, a lot of power, and they are very kind on this paper, not to say that probably the sample has been molten, because the power is really high. TPPM is improving. Spinel 64 that I didn't detail, which is, I would say, a recursive approach of TPPM, is doing something that is comparable to TPPM, probably slightly better in many cases. Here in this figure, it's not that better. XIX, I don't know why they have chosen that example. They claim that there are many artifacts that are coming in the XIX case. This is not true for all samples, and this is the result they obtained for Pizarro. That is really definitely a very good result. Actually, with this in mind, the question is, as you are manipulating the dipolar interaction, this dipolar interaction is absolutely sample dependent. So it is difficult to say that you will end up with one of those schemes that will be the best. However, what is to be explored is for given classes of sample, you have to make your choice. So I wouldn't say that none of the claims here are wrong or right. They are probably all right. But the question is, what kind of classes of sample are you dealing with? And if now you are facing with a new class of sample, probably at least at the beginning, you will have to tune a little bit your decoupling scheme to your samples. Now, I would like to go to two other items. Decoupling with quadrupolar nuclei has been thought for a long time to be something impossible or difficult. And Laurent Delevoye in Jean-Paul's group has shown that actually it is possible, a little bit in the same spirit that you have seen for the recoupling. But in this case, you're not going to apply the radio frequency on both channels, otherwise you will recouple. You have to apply it on one single channel. And since then, it's true that it is difficult to think that you're going to study samples that are containing quadrupolar nuclei without, when you're observing phosphorus, fluorine, proton, spin 1/2, to think that you're not going to decouple the quadrupolar nucleus. But for years and years, it has been a belief that actually we couldn't do that. So on nanoporous compound and on zerotic materials where you're having T sites that are different with aluminum and silicon, but for microporous aluminophosphate, if you're having all things together, J coupling, D coupling, quadrupolar coupling, this is probably the case where you cannot look for an automatic answer again. This is something that is related to your material. Why do I say such a despaired opinion? Because if it's not automatic, is it really worth doing a measurement, something that will be very complicated? But there are many cases where you cannot address those questions by any other means. So actually, yes, you have to know that if you're asked to characterize such materials, then with complex interactions, you have to be prepared at home to have the forces or abroad to have collaborations to be able to face those problems. And I would like to treat now an example where the consequences of decoupling are much broader than what it has been thought. This is, again, a compound that has been working in my laboratory for years. This has been given rise at many papers on methodology because we knew almost everything about that material, but we wanted to explore the different techniques and how they worked. It's a simple crystal. It's not really nanoporous. It's close to be nanoporous, but the pores are too small to call that nanoporous. But the spirit is just the same. It's made out of one unit. The unit is not a molecule because I've cut bonds, covalent bonds here, and this is an infinite network. Now the question is the following. how far can we go in decoupling? What is the impact of decoupling on simplifying NMR spectra? We wanted to do a fluorine to phosphorus experiment, CP. 2D experiment, so 90-degree pulse, contact, acquisition on phosphorus, and then evolution on T1, measurement on T2. So what we did was just to do the experiment 1D, and this is this spectrum. Now, the question is, we said, okay, but we are having in the pores ammonium entities, so protons. So why do you keep dipolar interaction between those two abundant case, fluorine and phosphorus, and protons are abundant also? If you keep that, then you will have all the dipolar interaction between proton, fluorine, proton, and phosphorus. So we decided to apply then a decoupling on the proton. And then this is what we got, a spectrum with a much better resolution. So we said, okay, why don't we keep going? Why don't we keep decoupling with aluminum? So we were measuring this, CP here, decoupling proton, and now decoupling aluminum. And then you see a spectrum that is much better resolved, definitely much better resolved. We just turned the experiment the other way and detected here fluorine. And we repeated the same game to do proton decoupling and then aluminum decoupling. And you see that you're improving the resolution considerably. Now look at what we have done and published several years ago, the same experiment, but we had only probes with 2 channels. So the experiment that you're having here is just a fluorine, and then we are going to get the fluorine to phosphorus experiment. Phosphorus is detected, fluorine is indirectly detected. The resolution on phosphorus is not that great, and the 2D is of that shape. We dared at that time, and we were accepted in JAX, to say that this spectrum can be described by those lines. Yes, we did, and the reviewers accepted that after some discussion, okay? Now, if you just apply the same decoupling scheme, the same experiment appears like that. So this is exactly what we had proposed in the paper. The resolution has been improved here tremendously, a little bit more than here. And this is not because you go higher in counterplot, no cheating in that thing. You're having definitely, even on 1D spectrum, the resolution. What is the meaning of it? Not that the spectrum is better resolved, is that actually you are doing many things at the same time. The first thing you do, you suppress interactions, you suppress them. But then, if you suppress interactions, what you do is that you're changing the value of the relaxation parameters. T1 row and T2 are affected by the fact that you're suppressing dipolar couplings. So when you're using a multiple decoupling probe, you are now entering into a game where relaxation matters. So for a long, long time, we thought that those parameters were just, parameters we couldn't change. But this is not true. We can change. And the effect net of such a multi-decoupling scheme are several-fold, actually. Why? Because you see that you can now devise decoupling schemes that are not located to one point. You can decide to decouple all over the way here, but you can restrict here during the acquisition. And you can also do some decoupling here in the fluorine. You could do that too. So first of all, we're developing now a wealth of pulse sequences that can use the multiple decoupling scheme. And what you do by just modifying the relaxation during those experiments is that you can introduce the relaxation as one of the parameters that can provide some information available on your sample. So, just to keep on the same sample, previous experiment published in JAX, okay? We had aluminum detected and fluorine here. What is the meaning of that spectrum? Actually, the question that was given here was the following. We have this crystal structure. We know it by diffraction, okay? So we know how to locate phosphorus, aluminum. Oxygen, some were OH, hydroxides. But you cannot do easily the difference between fluorine and hydroxide in diffraction. They are isoelectronic. So if you do something, then you will get something that is X. X could be OH or fluorine. So the question was, actually, do we have domains where you have fluorine on the bridging side, or do we have a statistical ensemble of that? So from the experiment we had on phosphorus here, we said this is consistent with a statistical distribution. With this, we had the proof, absolutely proof this is a statistical distribution. Now, you can, again, in this unit, you can detect aluminum. You have two types of aluminum, a 6-coordinated one, a 5-coordinated one. And the question is the following. If you are having fluorine here that is bridging this aluminum and that aluminum, then you will get cross peaks. They will be connected to both. And here, if you are having a terminal one, then you will get here just one cross peak between the aluminum 6 coordinated and the fluorine. So actually, this one was easy. A unit with hydroxide in the middle as only one type of signal, which is a fluorine terminal to a 6 coordinated aluminum. But a case where you are having the fluorine in the bridge is having the bridge here and a slightly different chemical shift for the aluminum 6 of this unit and the fluorine. Okay, so again, this is what we discussed and explained at length. Now, this is the experiment that we did with J couplings. So, as you are detecting now fluorine instead of aluminum, the experiment is transposed. And if I transpose the experiment that we have done before, you see that the resolution has nothing to compare. What is the net result of that? The net result is that both experiments are just proving one thing. In solution, when we crystallize this compound, we are having units without any bridge, one single type of unit. Actually, when the unit goes into the crystal, you're forming a bridge. But this bridge, the aluminum is 5 coordinated, could be water, hydroxide, or fluorine. So actually, we had, through the resolution of the 2D experiment, getting a hand on the last aspect of a mechanistic formation of crystal. What is considered as impossible is just to know how the unit in solution just jump into the crystal. We know that this is considered to be impossible, but if you are having the resolution that you can achieve by decoupling here, then you can even access to those detailed cases. So what I would really like to emphasize at the end of that a little bit shorter talk is that not only you can devise different scheme for decoupling, not only you can devise some multiple decoupling scheme, but those multiple decoupling scheme are helping you to play with an information that you were believing before that it was impossible to play with, relaxation times. So this is a point that is just emerging since triple irradiation probes have been devised. We are having a 4-channel irradiation probe. Now there is a new design for 5 irradiation probes, and for those people that are working on inorganic materials, 6 irradiation probe would do probably a very, very nice job. But if you want to do that, do not forget one thing. You cannot apply the coupling scheme that will be extremely demanding in terms of power. Because if you put the power on number 1, number 2, number 4, number 5, your probe is going to die immediately. Okay, so you have to think of probe development and of scheme for decouplings that are saving a lot in energy, so you can take advantage of those aspects. So this is, in a way, a shorter talk, but I'm getting tired now. So I would like, again, to convince you that this is really a field where if you have understood that with some rules that are not so difficult, with the combination of them, you can write like a composer an absolutely beautiful music, the music of the sound of atoms. And out of that, you can discover, this is an image that I'm always using in Paris, if you are located in the Jardin du Luxembourg and you are listening at the roam of the city, all the noises everywhere, you can listen to someone singing into Notre Dame, and then you can deduce its architecture. This is what we do in NMR.
Bueno, damos las gracias al doctor, pero si antes hay alguna pregunta. ¿Allá hay una pregunta? ¿No? Por favor. Aquí en la tercera.
Thank you very much. Oh, thank you very much, Francis. I have a question about multiple decoupling. There should be some limitation for the RF power, and maybe we have to avoid the Hartmann matching condition to apply multiple when we apply multiple decoupling. Could we have a practical guide to how to set up such a multiple decoupling? Oh, sorry.
It's okay. Is it working? Yes. Actually, the main problem is not to choose schemes for decoupling optimization that will have too many parameters. Because if you go to 1, 2, 3, 4 irradiation and through 3 triple decoupling, then you may spend 3 or 4 days optimizing, and then at the end, okay, you have a beautiful experiment, but it's a very expensive one. So the case there, first of all, the first condition is to get a very good isolation between channels. In the case of proton fluorine, this is always a delicate problem. But this didn't work that badly, and actually here we used only XIX for the 2 spin 1/2 and multiples for the case of the aluminum one. So let's say with sensitive nuclei like those, the optimization is done within 2 to 3 hours, just for optimizing. But in this case, we didn't go through, I would say, a systematic approach in order to deduce some theoretical hints. We didn't do that. Once again.
If we apply XIX to both channels, are there any interference for, how to say, the pulse length?
It could. It could. Okay, we thought of it, okay, so we were a little bit afraid of those interferences, but in this case it didn't happen. And so Yeah, it depends on the interplay between the residual dipole, the J coupling, and this, unless you do all the calculation before, which is not at all what we wanted to do. What we wanted to do is just to show that it works. But we were maybe lucky. I don't think so. I mean, because since then, we have done many triple irradiation experiments, and they do work. There is one limitation that is not in your question, is when do we stop improving? And there are cases where your material is distributed. And you improve the resolution, but at a point you touch at the limit of the periodicity of your material. So actually this is one of the cases where I'm not totally sure that we can push to the infinity, to Dirac mode. That would be great.
Now I have a probably very naive question, but in the sequence that you show at the end, you are not decoupling the fluorine from phosphorus, but no. you don't see the scalar coupling. Why?
Yes, yes and no. Actually, we had a strategy. In which order do we have to go for decoupling schemes? And the question is, the first one is really the most abundant. So the decoupling is really something important. You have to reduce that. That was the proton, okay? And then the second in the row was phosphorus. It was much less dense, and then we obtained quite good gains. And then for the fluorine, we tried several times, and then no real improvement on this specific experiment. In other experiments, yes, we definitely did get improvement, but in this experiment, adding the fluorine was doing nothing. So we have done it, but we have no further improvement. But this is a case where the fluorines are very diluted. There are not many of them, because on one unit you are having one terminal fluorine, and then you have to go to several other units where you can find two, not many with two, and the majority with one. So this is reasonable. But for a fluorinated polymer, your question is absolutely irrelevant. Please. Oh.
¿Alguien más? De este lado.
You say something about oxygen.
Yes.
In organic compounds, we have hydrogen, carbon, nitrogen. What about oxygen?
Sorry.
MAS.
Sorry, I didn't get the last part of the question.
Why your expression about oxygen and MAS technique?
No, oxygen is very good nucleus if you know how to label it. You have to label, because the sensitivity of oxygen is awfully low, 0.37%. So this is really a low, abundant nucleus. The frequency is medium-low, it's not very low. And then the interactions can be quite dominant interactions, or chemical shift, very large range, quadrupolar CSA. And it depends on which kind of situation you are. Silicates do not behave at all, for example, like carboxylic acids or amino acids. So oxygen is probably one of the nucleus that is now expanding very fast. It is definitely, there are some groups that are definitely using oxygen-17. The price to pay is the matter, the cost of the enriched water or enriched compound that you're using, and the cost of doing the selective synthesis with oxygen-17. It's much more expensive than normal labeling that people do in biology.
Thank you.
Okay. In my group, you are working a lot on oxygen 17 for material science. Okay, so it works, but it works mainly on high field spectrometers because if on a 400 it's most of the time too broad. So we use an 800. For the application of oxygen 17 to biology, to my knowledge, it's done by a Canadian guy, I think Gangu. He's working a lot on this. So if you want to apply, to use oxygen 17 for biology, I can give you the address of this guy. He's very good and applying this very well.
Bueno, si tienen algunas dudas más, pueden platicar con el doctor más adelante durante la comida o en los recesos siguientes. Thanks a lot for...
Thank you very much.
Gracias. There are with typical candies. And
these are beautiful about Puebla.
Puebla.
About Vida Eterna. Actually, I gave a talk with this picture. So I'm very pleased that you did.
Thanks a lot. Quiero comentarles que a continuación nuestra sesión va a ser la comida. Todos están invitados a pasar al salón donde tomamos el café. Ahí va a ser la comida. Y por favor les pido puntualidad para la segunda sesión de nuestras conferencias. Gracias.